Change just one halogen atom and the same carbon chain can flip from harmless to a highly reactive in your JEE paper. These halogens are the secret switches of JEE and NTA as they control the mechanism and rate of reaction and also the product produced. Hello, my dear JEE aspirants. My name is Gaurav Sir and I welcome you all to this amazing chapter of Alkyl and Aryl Halides. But if you promise to be with me in this video till the end, then I'm going to make this crucial chapter such easy for you that it will definitely give you at least one correct question in JEE Mains. And this will also be helping you for your JEE Advance. And this is the starting chapter of your class 12th organic chemistry. So it will definitely be helping you for your boards as well. But you will be requiring selected questions which we have handpicked for you, which are the most expected questions of JEE. So you can download all those practice sheets, the handwritten notes that I'll be discussing over here. From where? Just go to the link in the description section where you will be directed to the amazing world of PW, which is also helping thousands of students like you to excel in their competitive journey. So let us begin this side of organic chemistry. To begin with, let us start with the classification of alkyl and aryl halides. Now, first set of classification is they are classified on the basis of number of halogen atoms that they contain. If they contain one halogen atom, they are termed as monohalides. If they contain two halogen atom, they are termed as dihalides. And if they contain three halogen atom, they are termed as trihalides. You can even find polyhalides. Now, second set of classification is done on the basis of halogen atom, the functional group, connected to a carbon. So that carbon decides the property of the C bond X, how it is going to be broken. So if that particular carbon to which the halogen is attached is an sp3 hybridized carbon, as in it is forming 4 sigma bonds, then to all those carbon bonded halogen we will now generalizing and writing them as Rx, and this Rx is actually alkyl halides for us. So these alkyl halides can further be classified as methyl halide because this carbon is containing no further bonds with carbon chain, and if that carbon is directly attached with one alkyl group, one carbon chain, then it becomes a primary or simply 1 degree alkyl halide. If this carbon which is connected with halogen is further connected with two different alkyl groups, now this R and R dash may be same, may be different, but if this carbon is connected with two alkyl groups, then that particular alkyl halide is termed as 2 degree or secondary alkyl halide. And similarly, if this carbon is attached with 3 carbon alkyl chains, then it becomes a 3 degree or a tertiary alkyl halide. Moving forward. Now, these they are also alkyl halide. If carbon is sp3 hybridized, you can term that organic compound as alkyl halide because its property will be same. So another type of alkyl halides are benzylic halides. Although it is containing benzene ring, but actually the general name for benzylic carbon is the carbon that is directly attached with benzene ring. If to that carbon halogen is attached, then you can definitely see this carbon is also having 4 sigma bonds, so it is also an sp3 hybridized carbon. Moreover, if you ask, sir, benzylic carbon can also have degrees? Yes, because this carbon is connected with one carbon chain, that carbon chain is of phenyl group, so this becomes a 1 degree benzylic halide. So you can obviously have 2 degree or 3 degree benzylic halides. Now, the third type of alkyl halides are allylic halides. Now, what's an allylic carbon? The carbon, this green color carbon, the carbon next to a double bonded carbon is generally termed as an allylic halide, allylic carbon. Now, if you'll ask, sir, the carbon next to benzene is also a carbon this carbon is also connected to a double bonded carbon. So sir, benzylic halide is a type of allylic halide? Yes. So allylic halide, this pi cloud, if it is of benzene, then this is also allylic halide. But this allylic halide is also generally termed as benzylic halide. Else, if this pi cloud is of any other organic compound, then that pi, which is directly connected to a carbon, if halogen is attached to it, then these particular alkylides are also generally referred as allylic halides. And similarly, they can also attain degree, like in this case. If these two groups are hydrogen, it becomes a 1 degree allylic halide. And if I substitute alkyl group, it becomes 2 degree or 3 degree allylic halide. Similarly, sir, this is also, although this is a cyclic chain, but this green colored carbon is next to a double bonded carbon. So carbon next to a double bonded carbon, if halogen is connected with it, then this green carbon is an allylic carbon, and connected halogen becomes a allylic halide. Moving to the next classification. Now, if the carbon to which halogen is attached is an sp2 hybridized carbon, then what it is generally termed as? It is generally termed as a vinylic halide. This carbon is sp2 hybridized and directly connected to halogen atom. Such a group is generally termed as vinylic halide, and such a carbon is termed as vinylic carbon. So we have some very famous example of vinylic carbon? Yes, your aryl halide, because this carbon of the benzene ring is also sp2 hybridized. So this sp2 hybridized carbon connected with an halogen is actually termed as aryl halides. So when we say alkyl halide, we refer to sp3 hybridized carbon bonded with halogen. And when we say aryl or aromatic halide, in that case the halogen is directly connected with the benzene ring. And mind you, the chemical reactions of an sp3 hybridized carbon bonded with halogen, that is alkyl halide, is different, while the reactions of an aryl halide is different, because the lone pair of halogen atom will be in resonance with the whole benzene ring, and thereby creating a partial double bond character in this C bond X, which will rather make the C bond X relatively more stable than a simple alkyl halide. So reactions of alkyl and aryl halides will be different, and hence for reactions we will be discussing them separately, and I'll be again making those resonating structures for you. Now moving forward, let us have, okay, one more classification, a general name per se, because some general names are loved by JEE. So next classification is of dihalides. Now dihalides are basically mostly found in nature of two types. One is a geminal dihalide and one becomes your vicinal dihalide. Now what does geminal mean? When two halogens are attached to a similar carbon, to the same carbon, and if the two halogens are connected to an adjacent carbon. So adjacent position in Latin is termed as, in English also it is termed as vicinal position. That person is in vicinity of me. So when they are at adjacent carbon, it becomes a vicinal dihalide, and when attached with the same carbon, it is called a gem dihalide. Now, the general name. Generally, these gem dihalides are termed as alkylidene halides, and the vicinal one is known as alkylene. Now because I have taken two carbon chain, because this is the famous NCERT example, let's say this is two carbon chain, obviously its IUPAC will be 1,2 dibromoethane, but NCERT, JEE, even your boards love asking you reactants by their general names. So for some compound, general names are very famous, hence telling you that general name. In fact, I have written that general name only. Now this becomes, because it is two carbons, so it becomes ethylene dibromide, and the geminal one becomes ethylidene bromide. Now what is the difference between their general name? This term ID, to which I have marked with a different color, and just to make you remember, gem, go to your basic civilized life. Gem, you refer to some diamonds or something. So I'm giving you a story, a mnemonic to learn it. Let's say you are roaming around, you find a gem, a diamond lying on a road. You will be rich in a second without making any effort. So what your friends will say, Eid ho gayi. So ID, when you find a gem, you will have Eid. So that ID is added in between. Let's say if it is any carbon chain, so it is alkylidene halide and it becomes alkylene dihalide. Moving forward. Now, after classification, there is a point that I'm right now making. In GOC1, we have separately discussed all the IUPAC rules with many questions, and we have also discussed isomerism. Although I will again be doing isomerism and IUPAC, but that I will be doing only through questions. So if you are not at all comfortable with IUPAC and isomerism, then you should definitely go to GOC1 video and at least spend that 50 minutes in that GOC1 IUPAC and isomerism part and then move forward with this video. Else I'm discussing it again but with examples. Now this is a very famous example of NCERT only, which says you have a molecule where you have a organic compound with molecular formula C5H11Br, and you have to draw all the possible isomers. So we'll draw those isomers and we will try to relate those isomers also, so that we revise isomerism also, and we'll name them, so we'll revise naming also for alkylides. Now first of all, as in GOC I told you, you do not have to learn the formulas of how to find du. Du can be thought of with a simple logic that degree of unsaturation, when you have a saturated carbon, the general formula becomes CnH2n plus 2. And if there is a shortage of 2 hydrogen, du becomes 1. If there is shortage of 4 hydrogen, du becomes 2. If there is shortage of 6 hydrogen, du becomes 3. Now this unsaturation is satisfied by, obviously one du is satisfied by either one pi bond or one cycle. So these du formula is the basic which will let you know that whether the carbon chain is straight chain, having pi bond or having cyclic structure. Now for example, we have this formula C5H11. So now you tell me, for 5 carbons, in order to be saturated, how many hydrogen we need? So 5 2 jet 10 plus 2, that is 12. How many hydrogen you have? 11. Obviously one hydrogen you have removed and substituted by bromine. So this becomes your perfect saturated compound with no unsaturation. So du is 0. Now JEE loves asking such questions. Now sir, now we know it is a saturated compound. Now how we will draw all its isomers so that we will not miss any? So do not draw the structures randomly, rather go by a process. Sir, what is the process? First of all, if you have determined it is saturated, count the number of carbon. It has 5 carbon. Make that 5 carbon straight away. So our first structure becomes drawing the 5 carbon chain in the simplest manner, that is straight carbon chain. Now sir, but we have to decorate this with bromine. Yes, I have not drawn the hydrogen because hydrogen will definitely be satisfied because it will be saturated compound, that I have already checked. So not putting those hydrogens, but we have to decorate this with bromine, and let us see how many different products we can get by substituting bromine. So obviously you can see this is 5 carbon, so 1 2 3. So definitely I'll be needing this straight chain 3 times. Sir, how you have seen? With practice you will also get to know. Now what I'm asking you to do is, let's say we put bromine over here. Now you take out your pen and copy and start writing. Now bromine is a functional group, but it is regarded as a branch and hence its prefix is used. So its name will be 1-bromopentane. If I add a bromine over here, the IUPAC name will be 2-bromopentane. If I draw that bromine over here in the 3rd carbon, I will name it as 3-bromopentane. So this becomes our 3 structures. For sir, add here, it will become 4-bromopentane. No, because then you will be numbering from this side. So this carbon chain will give you these many structures. Now I have named all these isomers for you. I want you to pause, and if you are not comfortable, then write them, because I've uttered them. This is 1-bromo, 2-bromo, 3-bromopentane. Now What about their relationship? What type of isomers are these three? Because these three have same molecular formula but different names, so they are different compounds. So what isomers are they? They are position isomers. So what are position isomers? When size of main chain and side chain is same, there's only main chain, so size of main chain is same, and there is only difference of position of functional group, which is bromine. Now sir, after that, how to draw? You have explored all the option of straight chain carbon. Now deduct, reduce, subtract one carbon. If you subtract one carbon from 5, how much carbons you will get? 4. So make a chain of 4 carbons. Make straight chain. Now, sir, but we have 5 carbons, so add 1. Okay. This cannot be added because 5 we have already done. 5 we have already done. If I add here also or here also, I'll get the same nomenclature 1, 2. And if added there, it will be 1, 2. So add anywhere. So done. Carbon chain we have formed. Now our job is to again decorate it with bromine, because this bromine we are still left with. So again, let us take this structure 1, 2, 3, 4. So I'll be needing this structure 4 times. Sir, how can you say that? With practice, my friends, you will also see it. Else I'm drawing it in front of you so that you may also be comfortable with it. Now all these are position isomers. Now moving to this one, let us decorate. Now bromine going over here will give you same name. You go and check. I'm writing it. Let's say over here also will give you the same name, because our main chain numbering will be starting from that carbon only. So this becomes 1 bromo 2 methyl butane. So this becomes our structure number. Okay, not 6, 4th. Now sir, these two gone. What else? This one. Let us number it 1, 2, 3, 4. I'm iterating its name. 2 bromo 2 methyl butane. So the names are different, so they are different compounds. Becomes our structure isomer number 5. Now sir, obviously now we can see that permutation combination which we are doing, but how to name it? 2 will be coming from that side, because lowest location is getting tied, but alphabetization will tell you that bromine, because alphabetically coming first, so this should get the second place, second number. So its name will be 2 bromo 3 methyl butane. Not there. So again another isomer, 6th one. Now what about the last one? Is it same? Let us name it and see. 1, 2, 3, 4. So it becomes 1 bromo 3 methyl butane. So how many more structures I form? 4. What is the relationship between all of them? Sir, they are also position isomers, because main chain and side chain are same, only position of functional group is different. Now if I pick any one from these 3 and if I pick any one from these 4, can you tell me relationship between them? They will be chain isomers, because main chain size of these 3 and main chain size of these 4 are different, so they become chain isomers. Sir, more isomers we have to draw. Let's see. We have explored the option of 4 members. Now deduct one more. How much you will end up with? 3 carbons. So let us again draw those 3 carbons. So this is 1, 2, 3. Now this position gone, this position gone. Why gone? Because 4 option we have already explored. The only way left is this middle carbon. So let us introduce 1 carbon in that and another carbon in that, because this will end up with the number of possible chains you will form. So we can only form chain till this carbon. So this is the last structure. You make any structure, it will be repeated. So this is the last structure we end up with, but we again have to decorate it with bromine. The central carbon is already having 4 bonds. Carbon cannot make 5 bonds. So if you substitute any of the carbon with bromine, you will get the same name. You can check for yourself, and I guess most of you will be clear with this also. Let us name that compound. It will be 1, 2, 3. So name will be 1 bromo 2, 3 dimethyl propane, and this becomes your structure, that is isomer number 8, having no further position isomers. So how many structural isomers we have? 8. We have even given their relationship. This one, pick one from any of these four, pick one from any of these three. So 1, 2 and 3, all these are chain isomers because size of main chain is not same. Now coming to the sir, can alkyl halides show stereoisomerism also? Yes, if they contain stereocenter. What is a stereocenter? If I have a restricted rotation, as in if I have a double bond or a cycle, then I may show geometrical isomerism. If I have a chiral carbon, that is a carbon which is sp3 hybridized and having four differently substituted bonds, then I, as a chiral center, will have the capability to rotate plane of a polarized light. So obviously I cannot see any unsaturation, so geometrical isomerism is not present in them, but they can show optical isomerism. So let us search for that also. Now this is an NCERT example, but I'm exploring everything in it so that you will be getting comfortable with IUPAC and isomerism just with this NCERT example, a very highly loved question, which is actually good also because we are discussing every logic in this with this question only. Now let us search for the chiral carbon. Now I am giving you a trick to learn carbon, to quickly detect chiral carbon. If a carbon is having two bonds of the same type, it can't be chiral. So think of hydrogens that it will be having. If it is having two hydrogens, it can't be chiral. So I'm just drawing in one so that you can quickly judge it. No, 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 no. Now why saying no? Because hydrogen, if more than one hydrogen present, then you cannot have four differently substituted bonds. So no chiral carbon. No, yes sir, we can think of. This is hydrogen, this is 1-methyl, this is propyl. So this carbon becomes chiral. Coming to third structure, no, no, let us check bromine, but sir, this is also ethyl, this is also, its alkyl group are same, so not a chiral carbon. This one, sir, H2, no, let us check this one. One carbon with the bromine, one ethyl, and it will have one hydrogen. So yes, this is your chiral carbon. Now, no, no, let us check. This one is having 2-methyl, hence not chiral, rest are not. No, no, let us check. Nahi sir, this is again having 2-methyl, so not chiral. Okay, let us check this one. This guy is having 1-methyl, one isopropyl, one hydrogen, and one bromine. So yes, this will also be chiral carbon. No, 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 because 2-methyl, no, because 2H2, no, because H2, gone. No carbon is chiral. So if J is going to ask you good question, how many structural isomers we made? 8. Now if question is asking you how many stereoisomers we are making, then each chiral carbon will have 2 optically active forms. One will be dextrorotatory and one brother will be levorotatory. Because I have counted one, I mean one structure is this only, it may be dextro, may be levo. So let's say if this is dextro, the other person will be levo. So 8 we have already counted. This will give 1 extra, so 9, because the one we have counted will be at least dextro or levo. So it will have one more brother. So how many isomer will be increased because of this chiral carbon? This is 1, either dextro or levo. So we will add 1 more. Now, so add 1 in that 8. So I have got 9, 10, 11. So if somebody is asking you how many isomers it has including stereoisomers, so answer will be 11. But if the question is simply asking how many structural isomers it is having, this formula can have 8 different structural isomers. Now last thing, let us do the classification also. You tell me the degree of alkyl halide. Now this is 1 degree because halogen connected to a carbon is connected with only one carbon chain. I mean this carbon is connected with how many carbon you contain. I will represent it as R, so it is a 1 degree alkyl halide. What about this? This is a 2 degree alkyl halide. Again it is also a 2 degree alkyl halide. This is a 1 degree alkyl halide. This carbon is connected with 3 alkyl groups, so it is a 3 degree alkyl halide tertiary. This is a 2 degree alkyl halide. This is a 1 degree alkyl halide, and this is also 1 degree alkyl halide. You may be anything, but I am 1 degree. Now, one more general naming. If 1 degree alkyl halide are also called normal group if they contain straight chain carbon, so this can be referred as a normal alkyl bromide. Secondary, we already know. Tertiary, we already know. One is neo group and iso group. What is iso group? This group. First carbon, second carbon, and the methyl branch and its free valency. This group is generally known as isopropyl group. This photo is very famous. And if this free valency is connected with an halogen, then it becomes an isopropyl bromide. All these general names also I have separately discussed, as I've told you to go to IUPAC and isomerism if you're not comfortable, and if you have seen it and if you know it, then this revision is definitely sufficient for you. Now, what is a neo group? The carbon next to a tertiary carbon. Now this is a tertiary carbon. This becomes a carbon next to tertiary carbon. If its free valency you have, then this becomes a neo group. How many carbons it is using? 5. So this becomes a neopentyl group. If bromine is connected, so it becomes a neopentyl bromide. These are all general alkyl group naming, which you should also know. Moving forward again. Now, discussing that isomerism and IUPAC both, but with questions, as I've said. Now, this is a JEE mains question. Let us do it. It is saying maximum number of isomeric monochloro derivative which can be obtained from, okay, you have to make a reaction of hexane as in 6 carbons, 2,2-dimethyl, and 5,5 also methyl. Okay, now you have to do chlorination. Now, sir, we have not studied reactions. The chlorination thing you know from class 10th. I will be discussing also this in preparation, but obviously this much we know. If you do not know, I'm telling you, we'll be discussing in later slides. Now, what does chlorination mean? Alkane, you subject sunlight, and we have done it hydrocarbons also. Alkane, you subject sunlight. What does sunlight do? Sunlight do free radical. Through free radical, what happens? One hydrogen gets substituted by one chlorine. Although that can happen n number of times, you can get polyhalogen substituted product, but generally mono substituted becomes the major product. So just using that logic of hydrocarbon and trying to do a question of IUPAC and isomerism. Now, I want to substitute. Now I'm removing this because this reaction part we know from hydrocarbon. I've also explained it again. Now, again, decorate this structure with 1 chlorine is ultimately the whole soul job. Now, sir, if these 3 carbons, 3 as in this one, this one, this one, if any of these 3 or if any of these 3 are replaced by chlorine. So what I'm doing is I'm replacing any one of them with chlorine. You will see for yourself, you will get the same IUPAC name. I'll just do numbering for this. So because this first carbon is also having a branch, so numbering will start from here only. So this becomes 1, 2, 3, 4, 5, 6. So this becomes 1 chloro 2, 2, 5, 5 tetramethyl hexane. So this becomes your 1 isomer, structure number 1. Now, what about structure number 2? Let us draw it again. These methyl groups are already there. Now we have explored these options. This carbon can't have an alkyl group and halogen. This also cannot, because it has already formed 4 bonds, so it cannot have 5 bonds. Now, if I add halogen here or here, you will get same IUPAC name. How I am judging it? Because it is also CH2, it is also CH2. If I add here, I'll number from there. If I add here, I'll number from here. So do the substitution anywhere, you will end up with the same structure. What will be its name? Its name will be 1, 2, 3, 4, 5, 6, as in 3 chloro. Rest every name is same. 2, 2, 2, 2, 5, 5 tetramethyl hexane. Now, these becomes your 2 structures. Possibility ended. Now, what the question is saying? maximum number of isomeric monochloro derivative which can be obtained by. Now it is saying maximum number of chloro derivatives. It is not saying the isomers. So you have to calculate all the possible products. Sir, stereoisomers are also different compounds. So ultimately, with the hidden word problem mystery, it is asking you to give the number of all possible isomers including stereoisomers, because stereoisomers are also two different compounds. So because it is asking to give number of all derivatives, so you have to include stereoisomers also. So structural isomers, we can see they are two in number. What type of structure isomer? Position isomers. But let us check whether it contains chiral carbon also or not. Now obviously in the first structure you can see you have no this carbon having chlorine is also having two hydrogens, so no chiral carbon. Coming to this one, obviously you can mark this having one chlorine, one hydrogen. Left side is a tertiary carbon, right side is a tertiary carbon. But this okay, this is a neo group. This is a carbon next to a tertiary carbon, so left and right are not same, so this becomes a chiral carbon. And because this becomes a chiral carbon, so this second may be dextro, may be levo. So how many isomers I'll add? 1. So 1, 2, and let's say this is dextro, then the third will be its levo rotatory form. So how many possible derivatives I have? Your answer will be beautifully 3. A shorter version of the question of NCERT, but definitely a JEE mains question. Moving forward now. Again the same question, so let us do it quickly. I hope you can also do it. So pause and do for yourself, but for those who still want more revision, I'm doing with you. The isomeric product by, again, monochlorination I have to do, but of what? 2-methylbutane. So this is 2-methylbutane. Now let us decorate it. Decorate it with what? Decorate it with chlorine. 1, 2, 3, 4. Sir, how you are judging? I guess now you should also judge. Replace chlorine in any of them. I'll get this. Substitute over here the second one, over here the third one, over here the last one. These are the possible structural isomers. All are position isomers. Now let us check the chiral carbon, because again question is saying isomeric products. If saying isomeric products not including everything, then calculate all possible isomers. So all possible isomers will include stereoisomers also. So let us again find chiral carbon. Now no CH2. Let us check this one. 1 carbon, 2 carbon chain, 1 carbon but with a chlorine and 1 hydrogen. Yes, this becomes your chiral carbon. So structure 1, this will be dextro, so 2 will be levo. So I have 2 structures, 2 products. Structure is 1 but 2 products. Now what about this one? No methyl group are same, so this is just the third one. Over here, yes sir, let us check this one. 1 carbon, isopropyl, chlorine and hydrogen. Yes, this also becomes chiral carbon. So let's say this is structure 4. It will be, let's say, dextro. So fifth will be levo. So counting 2 over here. Now what about this one? No. What about this one? Sir, but this carbon is having 2 same methyl groups, so not chiral. And obviously rest are having CH2, so this is not chiral. So this will be just the 6th one. So how many total isomers we have? 6. If the question asks you how many structural isomers it has, 4. But how many total isomers it has? 6, because 2 of them are chiral. So we'll be adding one more. So answer is beautifully 6, a JEE mains 2024 question. Moving forward. Now again a question, we'll just do it the same question. I guess now you will be learning with practice also. 2-chlorobutane. Okay, now you already have a chlorine. This is 2-chlorobutane. And you have to again substitute. As I've told you, alkyl halide may be substituted by more halogens. Now if the question is asking you it is making 2 halogens, the product is also telling you that it is C4H8, 4 2 8. Sir, 2 hydrogen is less, but those 2 hydrogens are substituted by chlorine. So DU, degree of unsaturation, is still 0. So it is still saturated. So how it will be saturated? You will be having 2 chlorine. 1 chlorine is already there. Add 1 more chlorine. Sir, what are the possibilities? I guess now you will be very comfortable in predicting that you will be decorating it in 4 possible ways. This will be 1, this will be 2, this will be 3, and this will be 4. So these are again 4 possible structures, but let us go to the English. Number of, okay, now the question is asking you optically active isomers. You have to now just, not all isomers, you just give the number of those isomers which are optically active. Again, a beautiful question. This is also JEE mains question. Now, first let us find out where we have chiral carbon. No H2. Let us check this one. 1 carbon, 2 carbon, chlorine and 1 hydrogen. This is chiral. So structure 1 is containing chiral carbon. So if it is chiral, 1 will be dextro, 1 will be levo. So how many optical isomers you already have? How many optical active products you already have? 2. Coming to this one, changing the color. Sir, no. This is having 2 chlorine, so no, no, no. So I'm not even counting it because this is not optically active. So why should I count? So I just have 2 now. This is a structural isomer but not optically active, so why I should count? So not counting. Now what about this one? Chlorine, 1 carbon with something, 1 methyl and 1 hydrogen. Yes, this becomes your chiral carbon. So because this becomes your chiral carbon, so 1 will be dextro, another one will be levo. But sir, it contains 1 more chiral carbon. Let me tell you. Look at this carbon. 1 carbon, 1 this bigger group, 1 chlorine and 1 hydrogen. So it contains 2 chiral carbon. But whenever you have 2 different chiral carbons and the molecule is symmetric, sir, symmetric as in you can number this structure from this side also and from that side also. So whenever you can structure name the number the structure from both ways, you should always make its Fisher projection in your mind. Fisher projection as in, sir, I've discussed all these things in isomerism. Fisher projection as in this. This is first chiral carbon, this is second chiral carbon. So let's say this is CH3, this is CH3, this is Cl, this is Cl, this is H, this is H. Whenever you have symmetrical positioning and you have more than 1 chiral carbon, then you will definitely land up with one case where you will be having an element of symmetry. So this becomes an element of symmetry, a plane of symmetry which can equally divide this compound in 2 equal halves. And such a form, although containing chiral carbon, but it becomes a mesoform which is optically inactive. So when it will be optically inactive, let's say when this one is dextro and this one is levo. So it will try to rotate clockwise, it will try to rotate anti-clockwise. If that one is levo and this one is dextro, then also they will cancel each other. So actually, if you have a chiral carbon, I can be dextro and levo because of this. I can even be dextro and levo because of the other person. But actually, I am counting for 2 of them. Out of them, let's say if I number from here or I number from that side, because it is having a symmetrical positioning by numbering from both the ends. So actually the number of isomers you should not always calculate using 2 raised to the power n formula. That's why I never tell that formula. Rather do it with common sense. What is the common sense? Let's say this is dextro, then this can be dextro. If both of them will be of opposite optical activity, then it will become a mesoform. So when both are same, it will be definitely optically active. Similarly, when both are levo, it will be definitely optically active. But the other 2 will be one of this only. So that it will, and the compound will be same. So this structure will be having 3 isomers. Out of them, 2 will be optically active and this one will be a mesoform. It will be a different compound, but this different compound will be optically inactive, the mesoform. So these 2 chiral carbons are producing how many optical isomers? 3. Out of those 3 optical isomers, 2 are optically active isomer and one is an optical isomer but optically inactive stereoisomer, which is the mesoform. Question is asking you what? Question is asking you to give the total number of optically active product. So optically active product, This becomes the third one and this becomes the fourth one. That mesoform I'm not counting. Why? Because it is optically inactive. Going to the last structure, a very good question. Going to the last structure, this is CH3. Yes, this carbon can become chiral. This is one chlorine, one carbon, one two carbon, one hydrogen. So this will also be chiral, and no other is it is not symmetric also, and no other carbon is chiral. So dextro and levo because of this. So this will give you fifth and sixth. Dextro and levo, fifth and sixth. So how many optically active products I have? Again, a beautiful 6. A very good question for you to practice. Just check. Moving ahead. So moving forward, let us discuss the nature of C-bond X bond and some basic physical properties of alkyl halides. Now, we know alkanes, sir, they are non-polar, so they must not be reacting. But sir, alkyl halide are very polar. And why they are polar? Because of the attachment of halogen. Now, we know that polarity, the property of an organic compound to react, is because of the polarity. And what is the measure of polarity? The measure of polarity is the electric dipole polarity is measured by electric dipole moment mu. The magnitude of mu, which is a vector quantity obviously, the magnitude of mu depends upon the charge and distance between charges. So, for a covalent bond, because of electronegativity difference, halogen being more electronegative will share the electron pair of cloud towards themselves, thereby making and accumulating a partial negative charge. Thereby, the carbon will develop a partial positive charge. So, more be the charge, more is the dipole moment, and actually dipole moment is predominantly a property of charge. Agreed. So if someone is asking you arrange methyl halides in order of their values of mu, so definitely we will be saying, because iodine is least polar, so CH3 bond I will have the weakest dipole moment, and you can clearly see also it is having the weakest dipole moment. Followed by the methyl bromide should have higher dipole moment. You can see that also. But there's a catch between these two. After that, methyl fluoride comes second, and who wins the race is methyl chloride. Now, I've already given you the values, but I do not want you to learn the value, but learn the trend. Now, why there is an anomaly? The anomaly rises because of the fact that although electric dipole moment is a property of charge, agreed, but it also depends upon distance between charges. Fluorine is most electronegative element. But chlorine is less electronegative, but it is not an electropositive. It has also got a decent electronegativity. So actually chlorine loses the battle when talking of electronegativity, but because fluorine is second period element, so bond length of C bond F is not small. It is very small as compared to bond length of C bond Cl. And because of the distance, the bond length factor, slightly fluorine becomes greater in magnitude of mu, which is the electric dipole moment. If you go to bond energy, obviously it is decided by the size. So bond energy is definitely decreasing down the group. But when we talk of electric dipole moment, then you have to learn this, that methyl chloride slightly wins the race and comes first. This is not valid for all alkyl halide. This data through NCERT I am only giving for methyl halides, which is very famous and you should know also. Moving forward now. Sir, you said electric dipole moment is a property of charge. We know that through chemical bonding also. So let us at least tell us what is the direction. So electric dipole moment is directed from positive charge to negative charge. Now, after knowing this, let us decode this question also. We have to arrange in order of mu. So clearly we can see this carbon and halogen bond, it will create a dipole upside. It will create a dipole downside. Therefore, we can say para has a mu. I mean, the net dipole moment will be 0. So it will be least polar, least mu. But what about ortho and meta? Sir, we know this much of physics. Let's say this is one vector, this is second vector. So vector addition is equal to under root of mu1 square plus mu2 square plus 2 mu1 mu2 cos theta. Not writing, it is a basic physics, you know that. And as the value of theta increases, over here theta is 60 degree. Over here it is 120 degree. And as value of theta increases, value of cos theta decreases. So order of mu will be, ortho will be having the highest dipole moment, followed by meta, and least will be para. These are some famous JEE mains questions. Moving forward. Now, let's say I have to again tell you the order of mu for these alkyl halides but polyhalogen derivatives. Now, let us first go to the basic structure. Now we know, so this carbon is a tetrahedral carbon. Okay, how we draw a tetrahedral carbon? So 3 bonds forming a triangle. Okay, I'm not writing hydrogen. 3 bonds forming a triangle and 1 bond at the top. They will form a triangular base and this will form a tetrahedron. Perfectly clear. But over here, let's say I have 4 bromine atoms, 4 bromine combining atoms. Then this much chemical bonding we know. If you do not know, I'm telling you, for a symmetrical system, if all bonds are similar, then resultant bond length gets cancelled. So we know, because it's a symmetrical structure, so its mu net will be 0. Now, if you physically try to do this mu net equal to 0 for a tetrahedral system, you have to do I cap, j cap, k cap. So no, I'm not asking you to apply such mathematics in chemistry, which is not even required. I'm giving you common sense to interpret this tetrahedron. How? Just go and look at this tetrahedron from here. You will see 2 bonds on one side of the plane and 2 bonds on the other side of the plane. Now, with that view, just stand in front of the copy. So this wedge represents 2 bonds coming out of the plane and dash represents 2 bonds getting inside the plane. Now, if I have all bromines over here, then we know that this vector addition and this vector addition, this vector addition and this vector addition, I mean, they are not getting added, they are in fact getting cancelled out. Now, sir, why you are giving this photo? Let me directly come to this. When you have only one bromine, let's say this is, okay, I'm sorry, okay, 3, 4, okay, this is CH2 and this is CH3Br. So directly come to this CH3Br when we have only one halogen. Sir, in that case, definitely, let's say you have 2 bonds out of the plane, 2 bonds inside the plane. Let us take this photo few times. Now, what I'm asking you to have in your mind, have a picture in your mind. Let's say this is bromine, hydrogen, hydrogen, hydrogen. Now, what is polarity of carbon? Sir, hydrogen is relatively electropositive. So this will be delta positive and carbon will be delta negative in front of hydrogen. Although this polarity is negligible. But just I'm telling you this, that this vector will going this side, this vector will go this side, this vector will go this side. Although they may cancel, but this vector will be getting added to the vector through C bond Br. And as you increase number of halogen atoms, like over here, let's say this is also bromine, this is also bromine. Although they will have a net vector addition in the side. But if I have another bromine over here, 1, 2, and this third one, then whatever dipole these two are creating, this guy will be cancelling that dipole. I'm not saying it is a square planar structure, but this symmetry you can apply to have a feeling, to have a logic that as number of halogen atom is increasing, we definitely know through chemical bonding that CBr4 is a symmetrical tetrahedral structure. And because it's a symmetrical tetrahedral structure, so its mu will be least. Now I'm telling you, as if you directly look to CH3Br, then this bromine, whatever dipole moment it has, the C bond H is actually contributing, although to a very small extent, but to a large chunk of ocean, they are also contributing small drops. But ultimately, this is having some dipole moment. Hence, I am saying it is having highest dipole. And as number of halogen is increasing, ultimately, as number of halogens are increasing, ultimately the electric dipole moment will be getting more and more cancelled up. So if I have 2, it is cancelled, but to a lesser extent. If I'm having 3, more number of electric dipole vectors are getting cancelled. And once you get CBr4, all the dipoles have got cancelled, and we know that a symmetrical structure is nonpolar. So the exact order of dipole moment for these polyhalogen methyl substituted polyhalides will be this. A very rude logic moving forward. Now, this is also common sense. Sir, bond length is same. Electric dipole is a property of charge. So use 3C through dipole only. I mean, the magnitude of charge only. How to see that, sir? This carbon is an sp3 hybridized carbon. Benzene carbon is an sp2 hybridized carbon. Now we know ultimately let's say chlorine is electronegative. So it will take delta negative and carbon has to take delta positive. So which carbon will be easily giving electrons to chlorine? This carbon, because it is relatively less electronegative. As S character is increasing, the electronegativity of carbon is also increasing. So let's say this chlorine has a delta negative of this much magnitude, and therefore this carbon will have a magnitude of this much delta positivity, because if I withdraw 100 rupees, I get minus 100, you get plus 100, because you have lost 100 rupees, I have gained 100 rupees. But this carbon is not easily giving up the fight with chlorine, so the magnitude of charge for this chlorine is less, and therefore here also it is less. So because the magnitude of charge separation is less, because this carbon, the sp2 hybridized carbon, is more electronegative, so who will have a higher dipole moment, sir? The simple sp3 hybridized carbon bonded halogen. And that's why if you look at aryl halides, they have lesser polarity also. So aryl halides, because of aromatic ring also, because of resonance also, and because of the less polarity in the C bond X, they are relatively lesser reactive as compared to simple alkyl halides. A very important logic, a very important conclusion which we are drawing right now for later reactions moving forward. Now, coming directly discussing about some basic physical properties which we already know through alkanes. Now, sir, as number of carbon chain increases, melting point, boiling point, density, all increases. So they all increases as carbon chain is increasing. All melting point, boiling point, everything else also will increase. We know this common sense, because as carbon chain is increasing, the possibility of the surface area will be getting increased. And even though carbon is a non-polar chain, but a non-polar chain can be attracted to another non-polar chain by weak van der Waals forces of attraction, and as surface area increase, that attraction force will increase. So density, melting point, boiling point, everything increases moving forward. Now, also we know this surface area we have spoken of. So as for isomers who have got approximately same molecular mass, for these isomers, boiling point is inversely proportional to branching, because as branching will increase, molecule become compact, and as it becomes compact, surface area decreases, so its tendency to attract its adjacent molecule will decrease, and hence boiling point decreases. We have done this in hydrocarbons also. Now, sir, solubility. We know whole of the carbon chain is non-polar. Due to availability of this polar C bond X, which is also not capable of forming hydrogen bonding, it obviously they cannot get soluble in water. But yes, if the size of carbon chain is very less, and if you increase the volume of water, then because water is a universal solvent, so they may get soluble. But ultimately, these alkyl halides are organic compounds, so they will be soluble in organic solvent and not water. So because the thumb rule of solubility is like dissolves like. So these are some basic physical properties. Let us try some questions on them. Now, decreasing of boiling point. So boiling point, you've already said, more be the carbon chain or more be the mass, because more will be the size. So let's say if carbon chain is fixed, who has the highest size or mass? Sir, down the group, mass and size both increases. So iodide will have the highest boiling point and fluorides will have the weakest boiling point. So this is a very clear-cut answer and explanation for us moving forward. Now, again, order of boiling point. These questions are very famous NCERT questions and very logical for JEE also. Now, let us do this for the first one. Bromomethane. So bromomethane is this. Then bromoform. What is bromoform? CHBr3. Like, what is famous? Chloroform. Chloroform is CHCl3. So bromoform, it's a general name which says CHBr3. Next is chloromethane. So C bond Cl, because hydrogen you do not show it. The contribution of mass is negligible. And next is dibromomethane. So I have, okay, this is also quite simple, because as I've told you, more be the mass, more is the size, more is the size, more is the boiling point. So obviously 10 kg is always tend to have a higher boiling point than 1 kg of any and everything. We only compare intermolecular forces of attraction when approximately molar mass is same. So because this guy has highest molar mass, so it will be coming first, followed by it will be coming second, followed by it will be coming third, and least will be this, just because of the molar mass. So this is a piece of cake for us moving forward. The second one says 1 chloropropane. So I have a propane, 1 chlorine. So this is, let's say, A. Now iso is a general naming. How to draw this picture? 1 first carbon, second carbon, a methyl branch, and thereby a free valency. So this group becomes isopropyl group, connecting a chlorine with it. So this becomes isopropyl chloride. Now 1 chlorobutane. Obviously this is also very easy. Carbon chain has been increased. So definitely who won the race? C. This C will be having highest boiling point. I'm talking for this one. C will be having highest boiling point. Now these are isomers, and for isomers 1, 2, which is more branched? So this is more branched. So because it is more branched, so its surface area will decrease, and because surface area will decrease, one molecule will be less attracting another molecule, and hence this guy will have less boiling point. More be the branching, less be the boiling point. So then A will come and least will be C. A very easy and very practical question moving forward. Now next question says, which among the following which have, okay, now melting point. You boil a liquid, but you melt a solid. For liquid, you have to always think of intermolecular forces of attraction. Agreed. But for melting, what do you actually melt, sir? We melt the solid state of that particular matter. And solids are basically decided by the effective packing they are having. We have already done this in alkanes also, again repeating it. So what solids are efficiently and very efficiently and tightly packed? Those solids who are meant to have symmetry. Even if you pack a suitcase, the suitcase that which is packed quite efficiently, effectively, I mean after stacking symmetrically, the stacking one jeans over another jeans, and that way your suitcase will be containing much more of your dresses and your suits. So it will become a highly efficient solid. So symmetry represents a better and a best solid, and a best solid will have a best melting point, I mean high melting point. So talking about the, obviously this one option we have is chlorobenzene, it will definitely have the least melting point also and boiling point also. Why? Mass. We always do all these common sense when molar masses are same. So because your mass is less, so you are definitely out of the race for boiling also, for melting also. So I'm keeping this option C out of here. It will be having least melting point, least boiling point. So first talking of melting point with you. So because for solid, because we melt a solid, so I'm telling you, because para is most symmetric, and symmetrical structure tends to have efficient packing. So because para is more symmetric, so one para can be efficiently packed with another para, and therefore because para is most symmetric, so it will be having highest melting point. This you have to know through common sense also. We have applied the same logic in alkanes also. So if somebody is asking you to have to tell the order of melting point, so definitely we know now that para will have the highest melting point. Post that, sir, ultimately for intermolecular attraction, whom we go for? If we have comparable mass, dipole moment, and we have recently seen ortho has a higher dipole moment. So ultimately you are expecting, sir, if I'm polar, then I'm attracted by another molecule by dipole-dipole attraction. You said para is non-polar, so if it is non-polar, then its polarity is net dipole moment is zero, so it will be non-polar molecule attracting another non-polar molecule by weak force of attraction. I'm agreeing to that fact, but again I'm telling you this, that for a solid, what is the most dominant criteria? Symmetry. So because para is most symmetric, so it has won the battle of having the highest melting point. Then you go by your intermolecular forces. Who was having highest intermolecular force of attraction? Ortho. So then ortho, and then meta. And in fact, if you speak of boiling point, and in fact, I tell you one thing, NCRT also gives information about melting point, but for boiling point, NCRT blankly says that they have almost equal boiling point. But for very good questions, you should know boiling point also. And for boiling, you also already know. For molecules having comparable mass, we already take consideration of the intermolecular attraction. So who has highest intermolecular attraction? Which will be most polar? Who is most polar? Ortho. So actually, ortho wins the battle. Now, followed by you have para, and least is again meta. Sir, but meta should be coming. So this is actually a fact which NCRT does not give, which you can have through the values, which you can only understand because this comparison is actually an experimental data. So if it is more to you, then you can leave this also. You can only learn that their boiling point is approximately same, but melting point of para is highest. Why highest? Because of symmetrical arrangement. The first method, the capital A, is from alcohols. Now we have some methods by which you can prepare these alcohols. The first two methods are, you react this alcohol with concentrated HX, it will give the OH will be substituted and you will be getting your alkyl halide. Now instead of that concentrated halo acid, you can take only HCl in presence of anhydrous ZnCl2, and this process is called Groove's process, which will do the same thing. Substitute OH and you get an alkyl chloride. Now the mechanism of this reaction is quite important, so let me discuss that with some extra points, but you have to know it, although for mains also you should know that. Now actually what the point is, what the logic is, this C bond O bond lengths are both are second period elements, so bond length will be very less. So you tell me, if bond length is very less, then will the bond be broken easily? No. So actually what happens is, let's say I have this C bond OH. Now I am not interested in the bond, it can be anything, because right now I'm discussing that this C bond O is very difficult to break. So in order to break it, what we can do is, I am using a Lewis acid, which is the actually function of this ZnCl2 anhydrous. Sir, in HX, in the first one in HX, you have not taken any Lewis acid. In that case, you will be getting H+. So instead, that Lewis acid action will be given by that H+, let's say Hi, because if you think of the reactivity of HX, then you tell me which HX can be easily broken. Sir, Hi will be broken very easily because bond length is high, so it is the strongest acid. So this Hi, with this Hi, I do not even need any Lewis acid, because that Hi is a strong acid. It will furnish sufficient amount of H+ ion. So what this H+ ion and Lewis acid is doing, actually what they do is, they protonate the alcohol, as in, we very well know this oxygen is rich in electron pairs. So any Lewis acid like the zinc cation or H+, they will do what? They will force this oxygen to give its lone pair, because it is definitely a base. And once this oxygen gives electron to Lewis acid, attains a positive charge. Now a positively charged oxygen is highly electronegative, and it will not even care that this bond length is very strong. It will break this C bond O bond and now will take the electron with itself. So the action of this Lewis acid is to break this strong C bond O, and ultimately this will result in the formation of this beautiful carbocation. And through GOC also we know, or else I'm making you revise that point, that whenever carbocation is formed, it is always the slowest step of the reaction, and because it's the slowest step, so this will be the rate determining step. Point number one. Point number two, whenever a carbocation is formed, it will take sufficient amount of time to get stabilized. First, it will be given an opportunity of having ring expansion. Second, it will be given an opportunity to rearrange to its adjacent carbon, and if its reactivity, if its stability is getting increased, then it will definitely do so. Now, again, I'm summing up all the GOC logics over here. Now, what is the groups that increases the stability of this carbocation? First, if a carbocation is attaining aromatic nature, it is most stable. Second, all the electron donating group due to plus R effect will be next most stabilizing electron donating groups, followed by count the hyperconjugating hydrogens. How to count hyperconjugating hydrogens? This sp2 hybridized carbon connected with sp3 hybridized carbon directly, all the hydrogens of those sp3 hybridized carbon will be giving their sigma bond C bond H. So those hyperconjugating hydrogens will then be deciding the stability, and at last we'll be applying inductive effect. But for mains, only inductive effect, if you know for these alcohols, you will get your answer, because it is also a test. A test for what? Now, first let me complete this, although I guess it is quite easy for you now. After the stabilization of carbocation has taken place, what is the attacking species? Sir, H plus or this Lewis acid has done its job. Now the Cl minus will come and will easily form the alkyl chloride. Now, if I'm specifically talking of concentrated HCl in presence of ZnCl2 anhydrous in the ratio 1:1, then this reagent is also termed as Lucas reagent. Why? Because this reagent has a practical use, that it can detect the type of alcohol used. Because through mechanism we can definitely say that alkyl chloride will be super fastly produced by what? By a stable carbocation. And now if I'm asking you that, if I am giving you 1 degree, 2 degree and 3 degree alcohol, so you tell me which alcohol will form the carbocation easily. So definitely I know reactivity of alcohol, because carbocation is formed, so 3 degree alcohol will be most reactive, followed by 2 degree, and least will be 1 degree. Now, one physical property which you should know is, whenever in such an organic scenario alkyl chloride is produced, then you can see that alkyl chloride. How? Because that alkyl chloride has a physical property of appearing as a white turbidity. A white turbidity, like when you take limestone powder and mix water, that turbidity, that dhund, that white turbidity is seen. Okay, so if alkyl chloride is produced, you can very well see through your eyes and say the reaction has taken place. Now 3 degree alcohol, because they will form carbocation very easily, so 3 degree alcohol when mixed with Lucas reagent will definitely create this alkyl chloride, hence will be creating white turbidity. How? Instantly, because carbocation is instantly formed. Why? Because it is quite stable. Which carbocation? 3 degree. Hence 3 degree alcohol gives white turbidity instantly. Now coming to 2 degree alcohol, 2 degree carbocation is less stable, so it will take quite some time. It takes around 4 to 5 minutes, but obviously it will be formed because it is also stable, and hence you will also again get turbidity, but just with the time lag you will be able to determine that whether it is 3 degree or 2 degree. Now technically speaking, 1 degree carbocation is not stable. It is actually not at all stable. So if you continue this reaction, this Lucas reagent test at room temperature, 1 degree alcohol do not react. So what we do practically is we start heating in order to obtain white turbidity. So by heating at room temperature, it does not take place. But if you heat, I've written that also, if you heat and heat it for like 25-30 minutes, then obviously this bond will break, because this carbocation is not at all wanting to be formed, because it is not at all stable, because 1 degree carbocation is not at all stable. It is not less stable, it is not at all stable. But because of that high temperature which heating will be offering, it will be formed and you will be getting white turbidity in a half an hour. Now, completing the sense of reactivity, so obviously we know Hi, because of bond length, is strongest, highly reactive, followed by HBr, followed by HCl, and I am not even writing HF because of the same fact, because bond length of H bond F is very small, so it does not break. So if it does not break, it will not even furnish this H plus ion for the protonation of alcohol, because unless alcohol is protonated, this oxygen will not attain positive charge, and if at all this oxygen is not attaining positive charge, the C bond X is not going to break, no matter how stable the carbocation will be. So we do not use HF. Again, going back to the table, this table I want you to learn by heart. Now, the two steps we have done, and now I'm telling you, whenever carbocation is formed and substitution is taking place, such substitution mechanism we have already discussed, it's a two-step process. It is termed as SN1 mechanism. I will be giving more details about SN1 while discussing reactions of alkyl halide, but these all are the details which I have given, but yes, some more extra details I'll be giving later. Now, talking about the other method is preparation of alkyl iodide and alkyl bromide in lab. Actually, in lab, what we prefer is, we take alcohol, we add their salts, let's say sodium bromide or sodium iodide or potassium bromide or potassium iodide, and use an acid. The best acid which you can inorganically use to form any compound is sulfuric acid, because its boiling point is quite high. So what we do is, this is a very perfect method to produce alkyl bromide in very good quality, in very good purity amount, which is lab method. How do you prepare in lab? You add a salt of NaBr using acid. You can either use KBr, I mean any bromide salt with sulfuric acid. What happens is a simple reaction, because I have Br minus over here, I have polarity over here. So this halogen easily go over there, and this OH is replaced in form of water, the byproduct of sodium bisulfate you get. Now, similarly, you can do for NaI. This NaI I minus will also come, attack this alkyl group, OH will be substituted. So these are just simple substitution reaction which you should know, because these are NCERT fact. Now, one point which I'm making over here is, you can see also from here, with NaBr I've used H2SO4. With NaI I have specifically used H3PO4. Now, sir, with NaBr I can use H3PO4. With NaBr you can use any acid. But with NaI you have to only use H3PO4 phosphoric acid. Why? Because for NaI, H2SO4 is not just an acid, it behaves as a redox agent. As in, I'll just give you the reaction, because that is also a beautiful fact, an inorganic fact actually. So you cannot use H2SO4 with NaI. Why? Because, okay, you do not know this inorganic fact, then you must have used in lab. Let's say you have used NaI with H2SO4. In order to obtain HI, obviously you will get HI, and the byproduct will be beautifully, and you will be very happy. Okay, I've created HI, now I'll get alkyl iodide. But no, because this I minus will further react with H2SO4 that is present in the medium, and will oxidize. From -1 state, it is getting oxidized to iodine, and this I2 at room temperature, it is a solid. So if I minus is not even available, how come it is going to attack that alkyl group? So actually no alkyl iodide is produced if you use H2SO4 with sodium iodide or iodide salt. Now, coming back to our discussion. Now, coming to uses of phosphorus halides, again an inorganic logic, but used and given in NCERT and loved by JEE also. Now, the phosphorus salts you can use are phosphorus trihalides also and phosphorus pentahalides also. if you use phosphorus trihalide like px3. Now this px3, again p bond f bond length is very less, so not breaken, not used. pi3 is actually unstable. Why? Because bond length is very large, so the molecule gets destroyed very easily. So it becomes very difficult to packet them in a reagent bottle and supply them in industries, because if I will be supplying that pi3, that pi3 will be anyway getting decomposed because of high bond length. So what phosphorus halides are practically seen and used? The intermediate one, PCl3 and PBr3. I guess the logic is quite easy. OH will be again substituted. Whatever X you have used, you will come, but the byproduct. Sir, if all X is gone, then all OH will be attained by this phosphorus, because this phosphorus is in +3 oxidation state. It will remain in +3 oxidation state. How? It will be accompanied by the OH from alcohol. So you will be getting phosphorus acid again in +3 oxidation state. So here byproduct is H3PO3, very important. Now some people say no sir, we have to even practically industries have said no, we want to create alkyl iodide also. You inorganic search for something, so a reagent was searched. What the reagent was searched is inorganically. Again we know a phosphorus, an allotrope of phosphorus called red phosphorus with molecular formula P4. When P4 reacts with X2, it creates PX3 in the runtime. So I'm not packaging that bottle, I'm creating that pi3 runtime. Obviously over here you can use bromine also, iodine also, but PBr3 anyway we can produce. So this is actually red phosphorus plus I2 is used. Why? Because PBr3 anyway you can packet it in a bottle, but pi3 is unstable, so we create pi3 in the runtime of a reaction. How to create it? Red phosphorus plus I2 creates that pi3, so react. Now pi3 created, so it will be directly reacting to the alcohol, producing alkyl iodide, and the byproduct is again same, H3PO3. Now talking of phosphorus pentahalide, only one pentahalide is known to exist in nature, because now here bromine also, because 5 bromine around a phosphorus is not at all stable because of steric crowding. Chlorine is of optimum size, that 5 chlorine can be rearranged around phosphorus, so PCl5 bottles can be sold in market. So what about PF5? Again P bond F will not break, so not used. So in pentahalides I have only used PCl5. Again the products are same, I will get alkyl chloride, but what are the byproducts? Byproducts are phosphorus oxychloride POCl3 and this HCl. This POCl3, it is very famous also. Can you tell what is its hybridization? Yes, this is sp3 hybridized phosphorus with a shape of tetrahedral geometry. Now this phosphorus oxychloride and HCl are actually the byproduct with PCl5. Moving to the last set of reactions. Now these are for some good questions, although this logic you should know. What? Thionyl chloride, which is SOCl2, is the best reagent to produce alkyl chloride. Why? Because as you get your alkyl chloride, you do not get any byproducts. Why, sir? Because byproducts are removed as gases in form of SO2 gas and HCl gas. What product you get is a pure alkyl chloride. Hence use of thionyl chloride is mostly preferred to do what? To create alkyl chlorides, because you do not get any impurity, because all the byproducts are removed as gases. Now there's a catch, some extra point I'm discussing about this, which is less asked, but still very good questions may be framed around it. Now the mechanism. Actually, if you simply used thionyl chloride, you get retention of geometry. Sir, what geometry? Let's say if this carbon to which alcohol was attached, it was a chiral carbon. Now we have discussed this chiral carbon. Chiral carbon has a property to rotate the plane of polarized light. Now, what is the characteristic of a simple? Although there are thousands of optical stereo center as an asymmetric center which can make a compound optically active. But for JEE mains, for NCRT, the most famous asymmetric center is a chiral carbon which is sp3 hybridized, forming four differently substituted bonds. So for example, If at all you are getting a question, then I'm just discussing this only, that let's say if the R to which this alcohol is attached, it's a chiral carbon. Now, if it is a chiral carbon, then if I have only used thionyl chloride, then the optical activity of that chiral carbon will be retained. Let's say over here I have not taken that case, but if this carbon to which OH is attached is optically active, let's say it will be dextro, so the alkyl chloride will also be dextrorotatory. But if I use SOCl2 in presence of pyridine, then the optical activity of that particular alcohol, if it was dextrorotatory, it would be reversed. It will become levorotatory, because inversion of geometry will take place. Now, why actually this thing happens, I'm just giving you a brief about it, not investing much time on this. Now, just a logic, it will help you to understand, have a feeling of organic chemistry. Now, let's say I have this alcohol, perfect sir. This is SOCl2, perfect sir. Sulfur having +4 oxidation state, I mean it is highly electron deficient, and oxygen because of presence of lone pair will act as a base. So this is again acid base reaction. I told you mechanism is nothing but attraction between plus and minus. So this oxygen lone pair will be attacking this sulfur, and obviously actually what actually happens is, firstly this pi bond, because pi bond is weaker than sigma, so first sigma will not break. This oxygen will be carrying that pi bond, and as soon as it attains electron, it will again give back those electrons, and chlorine will be removed in form of Cl- because bond length is high. Because bond length is large, it will be easily broken. So I'm not showing that also. I just remove that because I want you to give you some beautiful picture which you can use as your notes also. Now, let's say that lone pair of oxygen is attacking this sulfur, and this chlorine is directly moving in form of Cl-. So leaving group gone, this Cl-, this H, this HCl I have shown with beautiful colors also. Now, this oxygen has given electron to this sulfur but has taken electron from hydrogen. So everybody is neutral, HCl gone. This is the product we have obtained. RO, RO, this S double bond over Cl. Now, let's say if there is no pyridine, then what? Sir, sulfur is still very electronegative. Why? Attached with double bonded oxygen, this is also electronegative. So do carbon has any capacity of holding electron from oxygen? No. So actually what happens is, oxygen will force carbon to give electron, and thereby offering that electron to sulfur. So this S double bond O and this double bond O will be forming SO2 gas, will be released. I told you. Now, HCl already gone. Now, let's say this SO2 is, as soon as this sulfur is attaining electrons, this chlorine will be taking electron from that sulfur at the same point of time, because the shape of this sulfur, because of the bent geometry of the sulfur, although we know there will be presence of lone pair also, but that lone pair will be aligned to to opposite direction, because it will be trigonal pyramidal, lone pair having higher repulsion. So this chlorine, because of the trigonal pyramidal geometry, will be aligned to that where oxygen is there. So as soon as oxygen is taking electron of carbon at the same point of time, this chlorine is also offering electron to that carbon from the same side, because oxygen has not left, and at the same point of time chlorine is also there in the game, because sulfur, this oxygen, this chlorine, because with respect to sulfur, shape is trigonal pyramidal. So what I'm trying to make you have a feeling is that as soon as this oxygen is taking electron of carbon at the same point of time through the same direction, this chlorine is also offering electron to that particular carbon. So ultimately I am getting R bonded with Cl with retention of geometry. Why? Because from where O has left the carbon of alcohol, from the same direction, from the same orientation, we have received, we as in the alkyl group has received lone pair from chlorine. So I am getting substituted at the same side from which the leaving group O is leaving. So this is called retention of geometry. So my optical activity is still retained. Now, if at all I use pyridine, Sir, pyridine is a base. I'm telling you. Nitrogen attached with a benzene ring, not a benzene ring. This is 5 carbon. The sixth carbon is replaced by nitrogen. This is the structure of pyridine. Now, through GOC also we know, and I'm telling you also, this lone pair of nitrogen is not participating in resonance, hence very much available, and hence it is a very good base. So let's say, because SOCl2 is still present, so this will be formed. But once this intermediate is formed, right now there is another donor who is willing to give electrons. It will give electron to whom? The electropositive center. What is the electropositive center? Sulfur with +4 oxidation state. So nitrogen as a base, this pyridine as a base will be offering its electron to sulfur. Then what I told you over there also, first what breaks is pi bond. Over there also, that's why I told you, first pi is broken. When the pi will come back, then chlorine will go. So similarly, now here I'm showing that, because here that process is making a difference. How? Let's see. Pyridine giving electron, pyridine getting attached and having a positive charge over here. Now, the pi of oxygen is broken because pi is weaker band, which will be broken. So this becomes O minus. Now O minus will give electron and chlorine is removed in form of Cl minus. Now because I have received electron from base, so this chlorine is very much given out in form of Cl minus, because we as a system has received electron from a base, from a strong base, which is pyridine. Now because this Cl minus has already left, it is not there. Over there, it was actually there as a trigonal pyramidal species just beside this oxygen bonded with carbon. But in presence of pyridine, this chlorine has already left the reaction species, and now this Cl minus is waiting for whom? You again come over here. Now nitrogen will say, I am a base, although I have participated, but now I am electronegative, I want electron. So if you can furnish electron, then I will be very happy to take my electron back, and I will be leaving the reaction as a catalyst, because catalyst is used but is regenerated at the end. So pyridine regenerated. As soon as this electron is removed, now oxygen will snatch electron from carbon, and again SO2 is still formed. SO2 gas is still formed. But now as soon as this carbon's electron is gone, now this Cl minus ion will be attacking this carbon. But from where? So this group is electron rich, minus. This Cl is already minus, and now this Cl minus has left their home, so now it is not inclined along with them. So this minus definitely has to approach this carbon from exact opposite to where these leaving group is present. So it will be actually a backside attack. So whatever the orientation, whatever the configuration of carbon would be there, it would be completely inverted, and we will be getting this backside attack of Cl bonded carbon. So what alkyl chloride will be obtaining? We will be obtaining a beautiful inverted product. Now moving forward, let us try to predict the major product formed when this alcohol reacts with HBr. Now we know HBr is an acid, will give H+, oxygen lone pair will attack these H+ ions and will form the protonated alcohol. Now we already know this C bond O is very stable, so it will not be broken easily, but after protonation this oxygen is very angry, and now it will snatch these electrons of carbon, thereby creating this carbocation. Now I guess it will be quite clear to you that we are having this carbocation. But sir, whenever carbocation is formed, it is always the slowest step and hence the rate determining step. In GOC also, in hydrocarbon also, and in previous slide also I told you, whenever carbocation is formed, it is always the slowest step. First we will give an offer to the carbocation to stabilize itself by what? By ring expansion, and post that by rearrangement. But now look at this carbocation. Let's say if you shift this to this carbon, you will feel it is 3 degree, but remember I said previously also, stability of carbocation is first decided by the resonance effect. Now we can beautifully see, because these lone pair are in conjugation, so this carbocation is actually resonance stabilized. So a resonance stable carbocation will not try to destabilize itself by shifting and getting a weaker electron donating group of hyperconjugation or plus I. So ultimately this carbocation will not rearrange and it is quite stable. So what is now going to happen? Now Br minus will be coming and will be attaching to this particular carbon. So this will be your, after bromine attached over here, will be your major product. So do not make this thing a point that always carbocation rearrangement will take place. Ultimately carbocation rearranges, because first, if it is directly connected to a ring, carbocation is directly connected to a ring, then it will undergo ring expansion to reduce the Bayer strain, and after ring expansion, if at all to the adjacent carbon it is getting more stability, so it will definitely get rearranged. But for all those understanding of stable carbocations, again and again I'm telling you, please make it a sequence. First CGOC, then hydrocarbon, and then, or else if you just want to know the very basic for the, because mains also ask some questions which are one liners, so those one liner questions you can easily make by having this limited knowledge also. Moving forward, now the first preparation of alkyl halides was from alcohols done. Second is from alkanes. Alkanes also, how to prepare alkyl halide from alkanes? By free radical substitution. How to do it? You use halogen. What halogen? Generally chlorination and bromination is done. Fluorination because it is very violent, so not done. Iodination because it is very slow, hence not done. Now chlorination and bromination, how to, sir? But alkanes are not reactive, so use free radical. So how to use free radical? By using excessive sunlight or heat, because in this scenario, even the C bond H can be broken because of high energy given by sunlight, or if sunlight is absent, use high temperature. So what will happen? C bond H will be homolytically broken. So what type of C bond H we are having in this particular alkane? Sir, if let's say if this carbon or this carbon both are 1 degree carbon, so if they lose one of their hydrogen, then the product form will be, sir, we'll be having 4 carbons, and Cl will be over here or over here or there. If you put chlorine anywhere, you will get 1 chlorobutane and the product will be same. Even you add chlorine here or there, it will be 1 chlorobutane. Now what else? Sir, if we substitute halogen, that is chlorine in this case, in this carbon or this carbon, it will be the same product. It will be 2 chlorobutane. Now generally monosubstituted products becomes the major product with the first step of chain initiation, where radical gets created, followed by chain propagation and chain termination. Now again I'm telling you, these all things I have discussed in alkanes, so I'm just repeating everything, but this repeating also will make your basic questions. But if a good question is asked out of it, then obviously you should go to the sequence, read alkyl halides first, this topic. If you just want to learn this topic, alkyl halides, read alkanes first, because in alkanes I have I have already discussed these mechanisms in great detail, although I'm repeating also, but I'm repeating without writing it. Now so out of these two, sir, but which will be the major product? Now we can clearly see this will be formed when a 2 degree radical will be produced, and this will be formed when a 1 degree radical will be produced. So obviously because 2 degree radical is more stable, so we'll say this becomes your major product and this becomes your minor product. But mind you, I told you in alkanes also, what generally you can give this, and generally maybe because of God's grace you will get a correct answer also. But my actual point is, the percentage yield of product that is produced obviously depends upon the stability of free radical, and therefore 2 degree hydrogen is more reactive than 1 degree. So this is less produced in lesser amount. But the reactivity also depends upon the number of hydrogen present. Like for example, now it is a good question, but again, because I said I have discussed everything in detail, but I'm using one question to give you all those logics. Now, for chlorination, the reactivity rate with 1 degree, 2 degree, 3 degree hydrogen is this. For bromination, it is different. If you do bromination, then bromination with a 3 degree hydrogen happens with a rate of 1600 times as compared to bromination happening with a 1 degree hydrogen. So sir, how to calculate percentage yield? We have discussed also, but I'm revising that also for you. Now, let's say we have this question. Now we are undergoing chlorination only. So first of all, what are the possible monochloro products, which we have already done in the previous slides, the JEE question, but they love these type of questions. But now I'm asking one more thing. You first tell me what are the number of possible monochloro products. Sir, if I substitute chlorine in any of these carbon, we'll get the same name. What name? Let us see. Sir, we have these 4 carbons, a methyl branch at the second carbon, and I just use this structure few times because we'll be forming those products. Now, if chlorine is going to this carbon or this carbon, you will getting the same name. What name? 1-chloro-2-methyl-butane. Let's say if chlorine is coming to this carbon, the name will be different, hence product is also different. This will be 2-chloro-2-methyl-butane. If chlorine is substituting to this one, it will be numbering will be from that side because chlorine is starting with a C, so alphabetization. So this is 2-chloro-3-methyl-butane, and if chlorine is going to this carbon, name will be 1-chloro-3-methyl-butane. So how many products we have? Sir, 4. I'm just talking of the structural isomers only. Now, if you see this A, it is a 1 degree alkyl halide. If you see this B, this is a 3 degree alkyl halide because this carbon is connected with 3 carbons. If I say this product is C, then this is again a 2 degree alkyl halide. And what about this one? This product D, it is also a 1 degree alkyl halide. Now, if I am asking you to now tell me what is the percentage yield of this product. Sir, in this question, it was very easy to predict. And it was just sheer luck that whatever through just knowing the degree, if you have given the answer is actually correct also. But actual point is, in order to actually estimate the percentage yield of product, what we have to do is, obviously, degree of hydrogen matters because free radical 3 degrees more stable, but number of hydrogen which has the capacity to undergo reactivity also matters. If you have one person in family, let's say for chlorination, he is earning 1 rupee per day. If you have another person in the family, he is earning 5 rupees per day, more reactive 3 degree. But let's say if in a family there are 6 person who are each person earning 1 rupee, they have less reactivity, but they are earning 1 rupee. So in total, the family is bringing 6 rupees at the end of the day. But if a family is having only one 3 degree hydrogen, then that family is, although the individual person is earning 5 rupees per day, but ultimately at the end of the day, that family is earning just 5 rupees, and that family which is having 6 1 degree hydrogen is earning 6 rupees. So percentage yield of that family having 6 rupees is high. So that is what I'm telling you, sir. But how will we calculate it? With common sense. Now, how to apply that common sense? I'm telling you. If I'm talking of this 1 degree, the product A, how many hydrogens are actually taking part to be willing to be get substituted by this chlorine? So these 3 hydrogens and these 3 hydrogens. Out of these 6, if you substitute any hydrogen with a chlorine, you will get this product. So what will be percentage reactivity with chlorination? During chlorination, 1 degree hydrogen reacts with a speed of 1 times. And how many people are actually participating in this race? How many hydrogens? 6 hydrogens. So its overall yield will be 6. What about this product B? Sir, B is coming from substitution of this hydrogen, and which is only 1. although its reactivity is high. How much? 5 times. But its contribution will be 5 into 1. What about this product C, which is a 2 degree, this one? So if we take this 2 degree carbon, 2 hydrogens will be participating. So these 2 hydrogens will be reacting, participating with what speed? With a speed of 3.8. So this becomes 3.8 into 2. So somewhere around less than 8, as in 7.6. Now, the last one, so this is also 1 degree. So how many hydrogens are actually participating to form this? So 3 hydrogen. 1 degree having lesser rate of 1 rupees, and 3 people are contributing. So total money that they'll be bringing on the table is this much. Now you tell me you can calculate percentage also. Add all these percentage yields. So 6 upon total will give you percentage. But you do not have to give the percentage. You have to tell which is forming the major product. So you can clearly see out of these which is having highest this. So C will be the major product because it is 7.6 times, followed by A, which is 6 rupees, followed by this 3 degree, which is B, and least formed product will be D. So it is not purely decided by the degree of alkyl halide, also the number of hydrogen participating. It is a good fact, you can leave also, but I have discussed all these things in detail, so again iterating them. Now, preparation of alkyl halides, we have done 2 preparations. First is from alcohols, done. Second is from alkyl halides, done. Now, third is from alkenes. Again, this also in alkenes chapter we have done, so summarizing all of them for you. Now, I've intentionally taken an unsymmetrical alkene, because to a symmetrical alkene you add one thing any side, another thing any side, it won't even matter, and many a times it means you get symmetrical alkenes also. But if not, so I've taken a unsymmetrical alkene. Unsymmetrical alkene as in, if you name this is having 2 hydrogens, this is having 1 hydrogen. Now, for addition of alkenes, the common mechanism, the most common mechanism, the rule which even NCERT gives is Markovnikov addition. I have written that also. But what is Markovnikov addition? When you have a double bonded carbon, negative part of attacking species goes to that double bonded carbon which is having lesser number of hydrogen atom attached with it. But do not go by this, go by common sense, because mains also tricks every time, not most of the time, every time. So how to think? Whenever you are using an alkene, and an alkene because of this pi cloud is an electron rich species. So this electron rich species will be only attacked by an electrophile first, preferably by an electrophile. Let's say we are reacting this alkene with an acid HX, halo acid. So obviously we know which halo acid which will be most reactive, sir, HI, because bond length is large, so it will be easily broken, so giving H plus tremendously, and the H plus will be attacking this pi electron cloud. Now after attack of H plus, what will be formed? Carbocation. So where carbocation will be formed, sir? Here, because it will be 2 degree. So 2 degree carbocation going over here, will it get further stabilized? No, sir, it is just the best possible configuration. So this carbocation which is stable also now will receive the X minus. So what product we will get? Over this carbon I have added H, so not showing, and halogen will be adding to this carbon. Why? Do not learn this Markovnikov, because of negative part will go to that carbocation which is more stable. This is simply Markovnikov addition, and this happens with all possible HX, but only with HBr, only with HBr. And in presence of peroxide and sunlight, what happens is this mechanism is when H plus was attacking, it was a electrophilic addition mechanism. But whenever you use HBr in presence of peroxide and sunlight, who becomes the attacking species? Br radical. So mechanism becomes free radical addition. And who attacks first? Br radical. So because Br radical is attacking first, so again logic is not changing. Which will be formed? So stable intermediate, but here intermediate is a radical, and because Br radical has attacked first, so it will be added to that carbon, because 2 degree radical is more stable, because radical is also electron deficient. And now this carbon chain having radical will further take H from another HBr, creating chain propagation. So ultimately what product we have got? We have got product in opposite to what Markovnikov has suggested. So this also is termed as anti-Markovnikov addition, but it only happens with HBr. I've discussed why with HBr and more the detailed mechanism, but again for that you have to go to alkene. If you are just wanting to do the basic mains question, then this is also sufficient. But moving forward, but I'm not discussing everything because that will unnecessarily create repeating one thing again, will hamper your time, also will make the video also long. So discussing precise things, but I'm mentioning every time that you should do what things from the previous lectures. Moving forward now. Sir, alkene can also form alkylides. Yes. As dihalide, yes, by addition of X2. How X2 are added? First, X plus attack, and X plus forms a cyclic brominium ion, followed by X minus attacking from the opposite side. So addition of X2 in an alkene is an anti-addition. And remember, if product formed contains 2 chiral carbon which is symmetric, then the keyword team. With trans alkene you get a mesoform, and obviously with cis alkene you get a racemic mixture. But when the addition is anti-addition, who does anti-addition? X2. With the mechanism also we have done. I am repeating everything, but for your JEE mains and for your basic questions you should just learn this. Whenever alkene is attacked by X2, either Cl2 or Br2, what you get is a vicinal dihalide. And one more information about bromine. Bromine in CCl4 is actually termed as bromine water, which has a orange-red color because it was existing. So its color would be existing, and after its reaction, it will be gone. So color will be gone. So decolorization of this bromine water is also a test of unsaturation. Moving forward, sir, if alkene is there, then can we do substitution also? Yes. Where? Allylic carbon. Where is allylic carbon? Carbon next to a double bonded carbon, because this carbon, if C bond H is broken homolytically, a free radical will be formed, and that free radical is not bad. It is in fact very good because it is resonance stabilized. But sir, free radical generally requires some situation. Yes. So if you create again high temperature or sunlight, free radical will be taking place. So for allylic substitution, what are the reagents? Cl2 in presence of sunlight, Br2 in presence of sunlight, and also one beautiful reagent, N-bromosuccinamide, NBS in presence of sunlight. What they do not do addition to alkene, rather there is a allylic substitution of whatever halogen you have used. So this finishes our preparation of alkylide from alkenes. Moving to last preparation. Now you have already seen, sir, we have prepared alkyl chloride, alkyl bromide a lot. So things which can be easily produced are cheaper. What you haven't produced, so fluorides, so we haven't produced even a bit. And iodides also we have produced less in number. So whatever is difficult to be produced industrially, it is expensive. So the last method of preparation of alkylide is halogen exchange, as in creating expensive halides using cheaper halides. So what are cheaper halides? Alkyl chloride and bromides. So these chlorides and bromides can be used as a reactant to produce iodides also and fluorides also. This is told to the scientific community by the scientist, hence a naming reaction. In order to learn this, the first is Finkelstein reaction, and as you can see, I have also marked it, this I. So you also, whenever you speak Finkelstein, give emphasis on this I. Finkel, Inkel, ing. So how does it help you? It helps you because Finkelstein forms iodide. So I. How Finkelstein forms iodide? Basic, you use alkyl halide, any halide as in alkyl chloride or bromide, use NaI or Ki, any iodide salt in presence of acetone. The simple substitution of I minus will be getting added, and this X will be leaving in form of X minus, going with the salt, and will be getting precipitated. So why it will be getting precipitated? Fazan's rule. What solvent you are using? Acetone. What solvent is acetone? Organic solvent. Like dissolves like. So organic solvent will be favoring which salt? Covalent salts. As the size of halogen increases, covalent character increases. So actually, because iodide is the largest halogen, so this is having high covalent nature. So because it is having high covalent nature, so this salt will be soluble in this organic solvent. But as the anions have got shortened, the ionic character is increased, and ionic compounds are not allowed to be soluble in covalent solvent. So these ionic salts will be getting precipitated, thereby shifting the equilibrium to forward direction, and you will be getting very high yield of alkyl halides. Sir, how to produce alkyl fluorides? In a similar fashion, but now with these alkyl chlorides and bromides, you have to use metallic fluorides. When you use metallic fluorides, again these fluorides will be doing the same thing and kicking out these Cl minus or Br minus and producing alkyl fluorides. Now, what are the example of these metallic fluorides? These are few examples which are given by NCERT: silver fluoride, arsenic, antimony, cobalt, and mercurous fluorides. So this finishes preparation of alkyl halides. Moving forward. So before moving forward, just allow me to add this one extra preparation of alkyl halides, that is from silver salt of carboxylic acid. Not there in NCERT, but few times has been asked by JEE because there's a trend. Now, if you take silver salt of carboxylic acid and make a reaction with halogen, let's say if you are reacting it with bromine water, Br2 and CCl4, then actually you get an alkyl bromide with a very common, without writing, I'm telling you that, remember, Br2 undergoes homolytic fission, and after that homolytic fission, the CO2 can also be released, leaving a radical at this carbon. So radical chain termination. Do not learn the mechanism, but just the process, that silver salt of carboxylic acid, when reacted with bromine water, forms corresponding alkyl bromide with one carbon atom less. Just like we have prepared alkanes by coal-based electrolysis. That's why, because it is being relatable with that mechanism of NCERT. Hence, JEE has also few times asked us. But a clear-cut point of reference. Now, that reaction is also naming reaction is called Hunziker reaction. But if you use, instead of bromine, if you use iodine in the same solvent, then it is observed that even the products changes, because the reactivity would have definitely been changed because of the radicals. So in such cases, it has been observed that chain initiation, chain termination definitely would be taking place, but that chain would be terminating via another R radical. So instead you get a beautiful ester, and this reaction is also a naming reaction termed as Bin-Baum-Simonini reaction. Please do not learn the name, but at least these two methods, the first method is not preparing alkyl halide, all the second method is preparing ester, but still, because there's a point of difference, so you should at least know this one extra reaction. Now moving forward to preparation of aryl halides. Sir, alkyl halides done. So for aryl halides also, now it is very easy, because all of you who have studied GOC and hydrocarbon through our previous one shots, now it will be very easy. For those who haven't done it, I'm iterating, but you will get a better feeling once you revise them. I'm again telling you, but for your, if simple question is coming, then this much information is going to help you. Now, the first method of preparation of aryl halide is via electrophilic substitution, because we know this benzene ring from upside also and from downside also, it is surrounded by pi electron cloud. That means it is electron rich. So this electron rich benzene ring can be approached by whom? Can be approached by any electrophile. I'm intentionally not putting any mark in the presentation because I want you to take it as your notes. So sir, then we know the mechanism. For step one is you have to generate an electrophile. So let's say we do chlorination and bromination. So in order to generate an electrophile, the plus what we use, sir, Lewis acid. So you can use either a D block salt like FeCl3 or an anhydrous AlCl3. What they will do, they will create the Cl plus electrophile. That Cl plus electrophile will be attacked by the ring, and after deprotonation, you get your aromatic compound, which is a substituted benzene. So in this case, chlorobenzene. If you use Br2 in presence of Fe, it becomes bromobenzene. Now, some extra information. Now, if you keep on doing this, Sir, now this has become a substituted benzene. Again, go to our GOC and aromatic logic. We have done it. This chlorine, because of the presence of lone pair, can act as a plus R group, but because it is having vacant orbital also, so it will be minus R. Moreover, it is minus I also. So ultimately, these chlorine will, that is attached with the benzene ring, will withdraw electron cloud, and it will be termed as electron withdrawing group. So are electrophiles very eager to attack this ring? No, because the ring has been deactivated because its electron cloud has been snatched by the chlorine. So chlorine is a electron withdrawing group. But if at all we have used excess of reagents, then excess of reagent would have created excess of electrophile. So if at all electrophile has been produced, its directive nature, where it will be going to the place where relatively electron density is larger. Relatively electron density is larger where? At ortho and para position, because ultimately it is an electron withdrawing group. It is withdrawing electron from the benzene ring. But whenever it is feeling free, it is feeling good. I mean, I'm just giving you a common sense that ultimately I'm taking 100 rupees from you every day. But once a while in a day, if I'm feeling good, I'll give you 1 rupee, I'll give you 2 rupee. But I'll not give 2 rupee to all the 100 people. I will take 1 rupees from all the 100 people, but I'll give those 2 rupees to few people. Similarly, chlorine and halogens having vacant d orbital are electron withdrawing groups. Point number 1. They are withdrawing electron and making the electron rich benzene ring electron deficient because they have withdrawn electrons. So these extra electrophiles are not very much interested. But by using these Lewis acids, I am forcefully creating those electrophiles. So now let's say another C plus have been introduced, where it will go. It will go to those places where this chlorine has at least given few electron density. So although it is minus R, but because of its plus R nature also, it will be creating some electron density at ortho and para position. That's why we say for these halobenzenes, the directive nature for the incoming electrophile is decided by the resonance effect. So where these extra coming electrophile will go at ortho and para position. And because para position will be having minimum steric hindrance, which is called the van der Waal, the hindrance between these bulky groups will be lesser in case of para, so that will become your major product, while this will become your minor product. So I have discussed the effect of electron donating and electron withdrawing group on benzene ring also during electrophilic substitution reactions. Now moving again forward, let's say if I do this n number of times, then sir, much number of electrophiles will be created, and if they are created, they will attack the ring, and you will get all substituted benzene with the formula C6Cl6, which is generally known as perchlorobenzene, which you can obviously form. How? If question is giving you benzene and it is giving you excess of this reagent initially only, then what you will be doing, sir? We'll be substituting all possible hydrogen. So this C6H6 will become C6Cl6, the perchlorobenzene. Now again, we have already discussed it in hydrocarbon, so I'm just iterating. Why we write dark over here? Writing dark or not writing dark will not change the product. But why generally JEE writes dark in order to specify that there is no sunlight? Because if there is presence of sunlight, then this benzene in presence of sunlight with this halogen will give addition reaction. Although that's a very vigorous condition, but in such situation, addition reactions of benzene may also take place, which will require a lot of time, but it will take place. And we have seen those reactions also. So what is produced? Addition product, which is C6H6Cl6. So that 666 product is very famous, although benzene aromaticity is gone, but it is still called benzene hexachloride, and it will have lots of geometrical isomers, and one of its geometrical isomer is very famous, which is lindane or gemexane, which is a powerful insecticide used in agricultural industry worldwide. So that we have already discussed in hydrocarbons. So I'm iterating everything, but moving forward. Now, one point I will but still make over here, because it is now actually related to alkyl and halides also. Now, the second point I'm making again in this electrophilic substitution reaction is, let's say now I do not have benzene. Let's say I have a substituted benzene. Let's say I have a toluene. I mean alkyl substituted. Sir, so this is also, now you have given us the logic. CH3 is what type of group? Sir, it is also electron donating group. This CH3 is electron donating group because of what effect? Sir, because of plus hyperconjugation. Sir, hyperconjugation just works like resonance and create electron density at ortho and para position. So now again, whatever electrophiles will come will go where? Will go at ortho and para position. And in fact, unlike chlorobenzene, which was actually an electron withdrawing group, but because electrophiles were created, so where they will be going at orthopara, but they will not be very happy, very reactive in going to chlorobenzene. But this is a highly activating group. So electrophile will be eager, will be dying to be going at ortho and para position of this toluene. Now, so why I'm mentioning this again is because of the fact that, let's say, if I have this Lewis acid, then I know electrophiles will be created. And that the who will be the electrophile? Cl plus. So Cl plus will be directed where? Sir, it's easy. It will be directed to, okay, it will be directed to ortho and para position, which where para will be your major product, because steric hindrances ortho is more. So that will be your major product, but you can report both of them now. Again, I'm telling you, if it is dark or dark is not mentioned, it does not even make any difference to the product that we are forming. But if there is presence of sunlight, then sir, we have already seen in the previous slides. What? Sir, whenever X2 is used in presence of alkene, alkene is a reactive group. The double bond of benzene is not even reactive. And in that reactive alkene also, we have seen in presence of sunlight, when X2 is used, allylic substitution takes place. And because there is availability of allylic carbon, so what product we will report, my friends? Allylic substituted product, as in this CH2 will get a Cl. Sir, if we do Cl2H nu, again one more hydrogen will be substituted, so it will be a geminal dihalide. Sir, if we do again, then because there is one more hydrogen, so 3 chlorine will come. This will also be used in later chapter of alkyl and aryl halides, but in later chapter of aldehyde ketones, I'm sorry, and it's an NCERT fact also. So what point I'm making from hydrocarbons, if I have benzene, if question is giving you benzene and using Cl2 in sunlight, then it will give an addition reaction, because addition product is seen in nature. But now we know through common sense that if we have a substituted benzene like toluene, that is, if I have a allylic hydrogen, then instead of addition, what will be happening in presence of sunlight? Allylic substitution. A very, very important point, a very important point of difference you should know. Moving forward to the last preparation of, sir, are I like finished? Yes. First is Se, and second set of reaction is Sandmeyer's reaction. Now, what is Sandmeyer's reaction? The starting material for Sandmeyer is a very beautiful compound known as benzene diazonium chloride. Because ultimately, we should know this benzene is an electron-rich species. So a minus cannot be approached by minus. And we know if we want to prepare halogen, halogen mostly exists as X minus. So that minus cannot be minus repel each other. But sir, we can generate electrophile. So electrophilic substitution we have done only. But if at all the halogen is approaching in form of X minus, in form of, if I am minus, then I'll be plus loving, so I'll be a nucleophile. So sir, benzene ring can never be approached by nucleophile. Very difficult. But this process, this reactant can invite any nucleophile, as in any negatively charged species will also be invited to approach this benzene ring if there is presence of this N triple bonded N. Because now I'm going to your chemical bonding. N triple bond N, sir, it is the most stable diatomic molecule. So we know no one has this capacity to hold no one has this capacity to hold this nitrogen gas. It will be in tremendous hurry to leave any of the atom. Let's say this atom is carbon of benzene. You be what you are. Because I am the most stable diatomic molecule, nitrogen gas, so I will try to leave you. And once this nitrogen will leave in form of nitrogen gas, it will leave a heavy amount of positive charge on the benzene ring, and this plus can now be approached by any minus, and hence it is a beautiful starting material if you want any minus, as in plus loving species, to approach electron rich benzene ring, because we have created a full positive charge on this electron rich benzene ring. Now this is created by whom, sir? This is created by benzene diazonium salt. How it is produced? It is produced using aniline. Aniline is reacted with nitrous acid. Now, one more inorganic logic: nitrous acid is a not, it is an not weak, it is an unstable acid. You cannot sell bottles of nitric acid because it decomposes. So what to do? We have to prepare it in runtime. How to prepare in runtime? It is prepared by mixture of NaNO2 and HCl. You can clearly see NO2 and this H. In the runtime, it will produce nitrous acid. When nitrous acid reacts with this aniline, the NH2 part gets modified in form of this diazonium chloride. Now you will ask, sir, why this? You said no one has this capacity to hold N triple bond N, but this benzene ring is holding. This is holding because of the fact that we have created ice cold condition, as in 0 to 5 degrees Celsius the temperature we have maintained, because we want to suppress the kinetic energy of this nitrogen gas so that it will not go away. So we have created ice cold situation to decrease the kinetic energy of this nitrogen gas to such a low value that it can hold. Moreover, if you can just see pi sigma pi, so if you can just see, the carbon is also holding this carbon. This is a beautiful resonating structure. Now then chlorine will leave in form of Cl minus, so you can also reach from here till here. Chlorine gone in form of Cl minus, this N will get N triple bonded in. So because of this reason, what I'm asking you is that the C bonded N is not just a single bond. There is an application of resonance also in it, because of which there is development of partial double bond character. If there would have been a normal alkyl group, then it would not have been possible for that alkyl group to hold this N triple bonded N group. So aryl diazonium salts are known to exist in nature, although not at room temperature, at ice cold situation. But if we have alkyl halide, it can't even hold this N triple bond. So why you are giving so much of details? Because this is also there in NCERT in chapter of amines. So because of resonance, aryl diazonium salt are stable, but even though it is stable, even though the bond order has a partial double bond character, but still nitrogen, in order to hold nitrogen, we have to create ice cold situation. Even you use water at room temperature, this nitrogen gas will move away. Now because moving of this nitrogen is very easy, so now let us use it as a starting material. So using it as a starting material, what are the reagents which Sandmeyer has offered? 3 basic reagents. If I use any of the cuprous halide, in such cases of cuprous halide, we can use cuprous chloride or cuprous bromide. So I'll be getting chloro or bromobenzene, nitrogen gas is released. If you directly mix this diazonium salt with Ki, just shake with Ki solution, obviously the temperature will be coming at room temperature, nitrogen gas will be gone. What minus we are having? I minus, so iodobenzene will be formed. Now fluorobenzene, creating fluorobenzene also requires some factual knowledges. What? Now in order to form fluorobenzene, first react with HbF4, fluoroboric acid. So fluoroboric acid is an acid, will give H plus and will form a salt with this diazonium salt, which is benzene diazonium fluoroborate. This Cl minus and H plus of fluoroboric acid gone, so here minus HCl is gone and we get a salt. Now a property about this salt is actually stable till room temperature. So even if you have made a reaction, even if ice cold situation is done, still this salt will remain as it is stable. it is one of the very few diazonium salt which is actually stable at room temperature. So in order to make fluorobenzene, now you have to further heat this salt. Once you heat the salt, now nitrogen gas will attain kinetic energy, will move away, leaving behind BF3, and out of that BF4 minus 1F will now be adding in form of F minus to benzene ring, creating your beautiful fluorobenzene. Moving forward, so moving to the chemical reactions shown by alkyl halides. Now, basically there are three set of reactions. First set of reaction being the nucleophilic substitution reaction. Second being the elimination reactions. Now I'm just briefing about them first. Elimination reaction as in, let's say I have an alkyl halide, so I'll remove this halogen and I will remove the hydrogen of the alpha of the beta carbon. Why beta? Because IUPAC general naming tells us that because halogen is a functional group, so where it is connected it becomes the alpha carbon, general name, and the carbon next to the alpha carbon is generally termed as beta carbon. So using some reagents, what we do is, technically we know also because we have read alkenes, it is a preparation of alkene. If you use a strong base, what happens is the elimination takes place and you form an alkene. We'll be discussing it again, but we have already done them in the alkenes chapter. Now, the other set of reactions are reaction with metals. Again, also already discussed in hydrocarbons, but again telling you, I'll be writing that also again. The Woods reaction. So in presence of metal, what happens? Metal have a tendency to lose electron. By losing that electron, what intermediate is generally produced? Free radicals. So those free radicals undergo chain termination and you get various types of products. So these are the two set of reactions which we have already discussed in hydrocarbons, but I'll be dealing with them again with few examples and basics later. But coming to the most important and most famous reactions shown by alkyl halides, those are nucleophilic substitution. Now let us understand them in detail. Now, sir, we already know that this carbon bonded with halogen, this C bond X bond of alkyl halide is quite polar. Why it is polar? Because halogen being electronegative withdraws the electron, thereby introducing partial positivity on carbon. Now, if at all there is a nucleophile. Now, what's a nucleophile? Which loves positivity, which loves electron deficiency, like the positivity in carbon. So this nucleophile approaches this carbon and kicks out the halogen. So halogen is removed in form of X minus and this becomes your leaving group. While the carbon which we had, let me make it with the similar color, the carbon which we had gets substituted by this pink color nucleophile. Now, this is the basic that we know, that we should know, that what is a substitution reaction. I remove one person from the table and I sit on that table. Now, there are many reagents who are capable of producing so many nucleophiles, and all those nucleophiles have the capacity to kick out this halogen as leaving group. Because if a nucleophile is giving electron to carbon, then it should have also an ability to give those electrons to a larger extent as compared to this leaving group, because we know every reaction is reversible. So if forward reaction is taking place, so backward can also take place. As in, there may be a case that this minus can again give electron to this carbon and reverse reaction would be taking place. So such a reaction will be not favorable for us in industry, because we have started something to form products, so maybe we'll be having some industrial use of this product. So actually what now, this is also a logic which is a direct outcome of GOC and chemical bonding that we know. Who is a better leaving group generally? So leaving group do not have to give electrons. So giving nature is a basic nature. So in general it is said that a weak base is a good leaving group. So whoever X minus is a weaker base, then the The basicity and actually basicity and nucleophilicity are two different things, but they are actually very important logic, but for very, very good questions. So as of now, I'm just telling you this, that what is a nucleophile which offers electron, what is a base which offers electron. But nucleophile give electron to carbon and base gives electron to hydrogen. Base doesn't care that it has to go deep inside the molecule and give to carbon. Base just wants to give electron, so rather base gives electron to the proton, hydrogen, small hydrogen. But what methodology I'm asking you to for mains also you should remember is who is a good leaving group. All those leaving groups are good which are relatively a weaker base, because they'll not be having a tendency to give. So if I'm not having tendency to give, so generally a weaker base is also a weaker nucleophile, but not always, because basicity and nucleophilicity always doesn't go side by side with each other. Moving forward, now I will be giving you a list of reagents which we'll be offering us with nucleophiles. So we'll be doing that list also, a very important list for JEE mains. But more important, that how this mechanism takes place. Sir, you have already told us, but chemical kinetics have shown us that the general mechanism with which these nucleophilic substitution takes place are of two types. First being bimolecular nucleophilic substitution reaction, simply represented as SN2. Now what is SN2 mechanism? Obviously you have a alkyl halide. Now I have deliberately made this alkyl halide as a tetrahedral structure, because if at all this carbon is optically active, then I am interested in the optical activity of the product. Because I am now interested in the stereochemistry of the attack, as in from which direction, from in three-dimensional space, how the nucleophile is approaching and why it is approaching, because loved by JEE mains also, advanced also, and your boards also. This proper thing is already given in NCERT as well, so pay very nice attention if you are listening it for the first time, else I'm repeating for all those who wants to revise. Now let's say I have this nucleophile which is OH minus. Okay, sir. This OH minus is getting into this alkyl halide, ultimately substituting this halogen and getting added. Now, you can definitely see if halogen is moving from this side, then I have made the attack of nucleophile from opposite side. That's why nucleophile is over here and leaving group has gone. Now, this mechanism is actually called SN2. Why? First point is it is a single step process, because this is the mechanism. Mechanism is attraction between plus minus. Sir, show us those attraction. I can see oxygen with my negative charge, so electron rich. I can see carbon with positivity. Okay, so plus. Sir, you already told us. So if this nucleophile is allowed to approach this carbon, sir, when it will be allowed? When the bulkiness of these groups are not large. If the bulkiness is not large, then easily this minus will be approaching to that carbon because of its positivity. But we also know minus repel each other. Now this nucleophile is electron rich, this halogen is also electron rich. So rather this nucleophile will be approaching this carbon of alkyl halide from a direction which is exact opposite. Now, because the moment this nucleophile is approaching the carbon, at the same point of time, this halogen, this leaving group, will be leaving the system. So remember, I told you, whenever a reactant becomes a product, thermodynamically it can be exothermic and it can be endothermic. But whenever a reactant is converted into a product, it always reaches only those reactant forms product whose intermediates has the capacity to climb this activation energy barrier. Remember? And in that time, an intermediate stage is formed, and that intermediate stage decides what type of product will be formed. So what I'm telling you is, it is a single step process. So there is no intermediate, as in there is no carbocation, carbanion, free radical, nothing is created, because in the single step, nucleophile is approaching and leaving group is leaving. So this attack has to be a perfect backside attack. So this attack needs to be a perfect backside attack. If attack is perfectly happening from backside, then only it can result to an SN2 mechanism of formation of product. So why I'm saying exact, because think of the intermediate stage. We know carbon is a tetrahedral. Let's say my hand is carbon, the one bond, second bond, third bond, and let's say this is the halogen. So whenever nucleophile is approaching from that side, obviously the nucleophile will also have repulsion. So it is approaching and leaving group is about to leave. Leaving group has not left completely. Nucleophile has not entered completely. So those three bonds will come in a plane. Thereby, what chemical bonding picture you have formed in your mind, sir? A carbon has just formed, actually it has only formed 3 bonds in the transition state. So if a carbon has formed 3 bonds, its hybridization state will be sp2, and the fourth orbital will be an unhybridized orbital. And what is an unhybridized p orbital shape, sir? It is a dumbbell. So just look at the transition state then. Once nucleophile is approaching and leaving group is leaving, this is coming, so shown with a dotted line. This halogen is going, so shown with a dotted line, because they have not yet formed the bond and halogen has not yet completely broken the bond. It is in a transition state, hence the orbital is showing it is an unhybridized p orbital. This guy is leaving and this guy is coming. So what can you say about the transition state of this carbon? Sir, it is sp2 hybridized. I have written that also. So this transition state says that there is no formation of carbocation or anything. Just backside attack is happening, and in a fraction of a second, what happens is the leaving group has gone, and this nucleophile has directly approached this carbon by inverting its configuration. Whatever its configuration was, let's say its configuration was like this, its configuration is completely inverted, just like the umbrella. If you carry the umbrella having downside curve, if you carry the umbrella in a huge storm, obviously it will just invert. So in a similar fashion, the configuration of this carbon has been completely inverted. This is obviously made public to the scientific community through some experiments, and therefore this inversion is also known as Walden inversion by the name of the scientist who has discovered this. Now, coming to the graph, sir, this is a chemical kinetics graph. You have already told us reactant have to climb an activation energy barrier. So climbed and formed product. But many people miss this. Nucleophilic substitution at first place is happening. Why? At first place, why this nucleophile at all is approaching that carbon? Because it is attracted by its positivity. Mechanism is largely at first place, it is because of plus minus attraction. So what increases the reactivity? Sir, more be the charge, more will be the reactivity. What students do is, for SN reactions, they only look at the steric hindrance, because initially even I had told you that if this nucleophile can approach this carbon, let's say if these groups are very bulky, they will not allow the nucleophile to enter. But whether they are allowing or not allowing, whether carbon is hindered or not hindered, at first place, why nucleophile is coming? Because of the electronic factor. So you should also keep this thing in mind, that while deciding the rate of reactivity for SN1 also, for SN2 also, and especially for SN2, because SN2 is just happening in a single step. So why at all it is happening? It is happening because this minus wants this plus. So who will increase this plus? Because as we can already see this transition state, can you tell me what this transition state is? Haan sir, this is one center, the carbon. This is another center, the nucleophile. This is another center, the halogen. So this transition state is a 3-centered system. But let us count the number of electrons associated. Sir, nucleophile is a negatively charged species, so it will be bringing its extra electron also. So there are two electrons, and the C bond X is formed between two shared electrons. So in total, I have shown those electrons also, 1, 2, 3, 4. So this is actually a 3-centered 4-electron bond. So 3 center having 4 electrons will definitely make this transition state an anionic transition state, electron rich transition state. So think this transition state is like a minus. So who stabilizes minus? Sir, electron withdrawing group. Moreover, you can think from this side also, this P is an electron withdrawing group. So what does electron withdrawing do? Withdraws electron. Withdrawing electron would make this positivity of carbon more in magnitude. So if this charge is increased, the approach of nucleophile will also get increased. All these things I'm mentioning are direct questions of advance. Obviously, mains also tricks you sometimes, and sometimes you get straight questions. But because I'm discussing theory, so discussing everything. Now, moving forward, we have already discussed. Let us summarize for all those students who are reading this for the first time. SN2 is a single step process, already done. Transition state has no carbocation. So because there is no carbocation, so there will be no rearrangement. It is a pentavalent, the trigonal species, the planar species of the sp2 hybridized system, one coming, one going. So the transition state is pentavalent. Not carbon is not having those electrons, but pentavalent as in one is approaching, one is going. So the arrangement is trigonal bipyramidal, so pentavalent. Now, obviously transition state is unstable. That's why it in a fraction of seconds it forms product. Remember, reactant reaches to transition state, the time required is the maximum. Once transition state has been achieved, the reaction takes place in a jiffy. Let's say a reaction is taking place in 10 seconds. Then the reactant to climb that activation energy barrier is maximum time. Let's say it is out of 10 seconds, it will be 8 seconds. And in a fraction of 2 seconds, product will be formed. So this transition state is highly reactive. Now, one thing I've already told you, electron withdrawing group does what? Electron withdrawing group increases the rate of reaction. Now, if theoretically somebody is asking you how they increase the rate of reaction, by decreasing the activation energy barrier. Now, you do not have to climb that much high because the electron withdrawing group decreases the activation energy barrier. Now, it is a chemical kinetics fact and common sense also, which you should know. Moving forward, coming again to this I've already written. Electron withdrawing group stabilizes the transition state, and if intermediate gets stabilized, it is formed easily. If it is formed easily, it will be reacting fastly. So for intermediates, the thermodynamic law of end products is not used. For thermodynamically, what we say, if somebody is stable, it will not react. For intermediates, we say if you are stable, you will be forming, and if you will be forming, then you only will be reacting. So more stable intermediate is obviously more reactive also, because that will be formed and that will be forming product. A very good point again. Now, okay, these I have finished now. Okay, now let's say you also can elemental effect is observed. What is elemental effect? Let's say I have chlorine with 35 mass number. Let's say I have chlorine with 37 mass number. Which leaving group is heavy? 37. So heavy person will move slowly. So if chlorine 37 you would have taken, the rate of reaction would be lesser. So this is just nothing but elemental effect, which is sometimes for good questions you should know this. Now, Walden inversion, I've already told you, when during SN2 complete inversion of geometry takes place. Now, it is a bimolecular reaction, as in molecularity of the reaction is 2. By what is molecularity? It is a theoretically, we have just now seen the mechanism. It is a theoretical mechanism we have seen, and that theory we have developed as per the experimental data. So what is molecularity? Number of reactant molecules in the theoretical mechanism, in the step of a reaction. So how many reactant molecules we have? So 2. This nucleophile, more be the nucleophile, more will be the rate of reaction, and more will be this alkylide, more will be the rate of reaction. So molecularity of the reaction is 2, but it is a theoretical thing which we are commenting by seeing the theoretical mechanism of a reaction. Now, so because it is 2, hence the name bimolecular. So it is a theoretical thing that I have also written now. This is chemical kinetics logic associated with organic chemistry. Now, what is order of reaction? When we write rate of a reaction using chemical kinetics, the rate law, the rate of reaction is equal to rate constant for this reaction. It is how it is calculated inside your home? No. It is always calculated experimentally. Hence written order is always an experimental concept. So we know experimentally we have seen for such reactions, rate of reaction is directly proportional to concentration of alkyl halide also and concentration of nucleophile also, raised to the power 1 and 1. This 1 and 1 how we have obtained experimentally. So what is order? Summation of powers of concentration terms of reactants in the rate expression. So rate expression has how many reactants? 2. What is the summation of power? 1 plus 1. So order of reaction becomes 2. But this 2 we have got because we experimentally know that power is 1 1. Now there is no kinetic isotopic effect as in, I mean this is also a good question, but telling you, let's say if alkyl halide has C bond H or it has C bond D, sir, it will hardly matter. C bond H is breaking or C bond D is breaking. It will have no impact on the attack of this nucleophile on this carbon. This H, this P is H or this R is D will have no effect because that bond is not even breaking. So if it is C bond H or if it is C bond D or if it is C bond T, any isotope will have no effect on the how the rate of this SN2 reaction is taking place. Now, moving forward to, so let's say the groups are very large. Let's say the groups are not at all allowing the nucleophile to enter. Then the reaction will not take place, it will take place. But how? Therefore, another mechanism is theoretically designated, and this mechanism is called unimolecular substitution reaction, which is simply represented as SN1 reaction. Now what it is? Now, you have your alkyl halide. It was observed when these groups were not large, they were very bulky. Still, in those cases also it was seen that this halogen was gone, substituted by this nucleophile still. Now, sir, what is this PPS? Actually, the mechanism, the SN1 mechanism is not one step. Now it is a two-step process. Where step 1 is, because I am bulky, because this carbon is bulky, so nucleophile is not allowed to enter. But if this alkyl halide is present in a polar protic solvent, now what is a polar protic solvent? Polar as in which has polarity, which has some dipole moment. Protic as in which has a capacity to give H plus. Because polar protic solvent, we all know the law of solubility, like dissolves like. Alkyl halide is an organic compound. But if this alkyl halide undergoes dissociation as in the first step which is suggested in the mechanism of SN1 is the alkyl halide C bond X gets broken, X takes away the electron forming X minus, and you get the formation of a trigonal planar carbocation. Sir, this is plus minus. So plus minus is a ionic composition of a molecule. So which solvent favors the formation of ions? Are polar protic solvent. Polar protic solvent like water, polar protic solvent like alcohol, because alcohol also have O bond H. Polar protic solvent are like acids, because acids also have O bond H. So polar protic solvent are polar, so they will shift the equilibrium to forward direction because they dissolve these ions more. Hence, reaction, they are dissolved, so reaction will be shifting to forward direction. Moreover, if let's say this P, Q, R are alkyl groups, then this carbocation formed will also be stable. So there is a double profit, in fact triple profit. First profit is nucleophile was not even allowed, so SN2 can't take place. Second profit is because solvent is highly polarizing, therefore it will enhance the formation of ions. Third profit, the carbocation which is formed, halogen anyway is an electronegative atom wanting electron, so you take electron and go away because this carbocation formed is not unstable. It will be a relatively stable carbocation because we are talking of substitution of some alkyl groups. Now, obviously, now through GOC we'll know, sir, carbocation formed, then sir, all the logic of carbocation of GOC will be happening. Yes. So if carbocation will form, it will be the slowest step, hence the rate determining step. I've written RDS also. So what is PPS? Presence of a polar protic solvent which favors reaction to proceed in forward direction, but because carbocation is formed, so it will be the slowest step, hence rate determining. So it will first get an option of ring expansion, next it will get an option of rearrangement, and once it has stabilized, then the second step will happen. What is the second step? Now, because if I was bulky, now 3 fingers, the leaving group. Now if I add a pen from the backside, I can do so because my fingers are quite thin. But if instead of these fingers there are huge balloons, sir, but then my hand will not even be visible. So this was the case in case of a bulky group. That's why nucleophile was not allowed to enter. But now if this leaving group has gone, I have become a trigonal planar species. So if I have a bulky group, the bulky group will be upside, it will be downside, it will be that side, it will be forming a triangle but in the plane. My carbon can be easily approached from this side also and this side also, because this thing has came to a plane. So now there is no repulsion from this side also and from this side also. So what will be the probability of this nucleophile of attacking, sir? 1/2, 1/2. So actually I will be, if I am attacking from this side, it will be retention of orientation, retention of configuration. And if I attack from backside, it will be inversion. So actually, theoretically, what we say, by knowing this as step 2, we say that in SN1, inversion and retention takes place equally. Therefore, if at all the product is optically active, as in this carbon is chiral, then 50% dextro is formed and 50% levo is formed. So overall, even the individual reactants are optically active, but overall product will be optically inactive, and such an optical inactive mixture is termed as a racemic mixture. We already know this through GOC. Now, one thing I have not written because advanced have asked it many times, not means, but you should know this. What? Practically, if somebody, theoretically I'm saying it is optically inactive, but practically if I'm asking you, are you sure this product will be in SN2? It was 100% inversion, agreed. But in case of SN1, let's say nucleophile is attacking 100 times. One of the time, in thousand of times, out of those thousand of times, don't you feel even one time backside attack can take place? I'm agreeing to the fact that they are bulky. However bulky you are, at least out of 1 in 1 lakh times, sometimes I can enter from backside, no? Moreover, because the leaving group is leaving, so it is having a minus over here. So nucleophile will be most probably more comfortable in coming from the backside only. So what my point is, you can obviously feel that through your common sense, common drawing logic, that out of those 1 lakh, 10 lakh times, at least one time, even a bulky, there is Kumbh Mela going on. But can't you feel that you can make by just adjusting? Some people have even made the darshan in that crowded place. All the people have not been stampede. Some of them have been. Similarly, that's what I'm telling you, that the nucleophile at least 1 in lakh of times can approach from backside. So if that is happening, then inversion is happening to slightly larger percentage. Therefore, it is practically, you should know, the product obtained during SN1 reaction is theoretically a racemic mixture, optically inactive. But practically, if I'm holding your neck, then you should always say that inversion happens maybe, backside attack would be happening a bit more. So if backside attack is happening, it is inversion. So inversion is happening, let's say 50.5% of the time. and retention is happening, let's say 49.9% of the time. At least some of the points will be taken by inversion. So inversion will be slightly more and retention will be slightly less, although very slightly. Now, a very good logic has been asked by advanced. Now, coming to the graph. Sir, chemical kinetics we know. So if a reaction is a two-step process, how you will know through chemical kinetics? Those reactant species will not be visible to your naked eye. Actually, we draw the potential energy graph. So whenever we have a two-step process, what is the product of first step? Carbocation. So in the first, activation energy barrier reached, and this represents that first step of the reaction has been completed, because whenever product is formed, after activation energy climbing, I have to go down, I have to come down, because the activation energy barrier is crossed by the intermediate. So actually for step 1, carbocation is the product. So it will be a graph like this: carbocation formed, and again an activation energy barrier. It is a smaller barrier, so that's why I told you formation of carbocation is the rate determining step. See, this is the real peak. So molecules will be taking much amount of time to climb this, but you should know this, that if a reaction is of multi-step reaction, then each step product is also a product for that particular step, although it will be intermediate for the overall step. And whenever product is formed after a peak in activation energy, you get a energy minima. This carbocation was acting as a reactant for the second step, so this was a minima, and again a peak is obtained, and then the final product is formed, which is your substituted product. A very important logic of chemical kinetics moving forward. Now, let us summarize SN1 also, because we have taken, I've discussed it to the maximum extent. Although if you discuss something in detail, you require time, so I took time. Now, it is a two-step process. Carbocation is formed, so rearrangement is possible. Formation of carbocation is definitely the rate determining step. As the polarity, now, as you have more polar protic solvent, the rate of reaction will increase, because polar protic solvent is actually moving the rate determining step forward direction. Racemic mixture is obtained. Theoretically, you should always say both retention and inversion occurs, but we know that inversion is happening 1 rupee more. No kinetic, though kinetic isotopic effect is observed, you have C bond H, C bond D does not even matter in SN1 also. Now, this is an important point. Branching. What people do is they think of carbocation. Actually, this is also an experimental data as per questions only I'm giving you. Now, whatever logic I'm saying, all these logic are actually your JEE mains, JEE advanced questions. Now, let's say I have these two alkylides and I'm asking you which is reacting more as per SN1. So what will be your answer? Actually, more be the branching, more will be the push to the carbon of alkyl halide to leave that halogen. Think of like this, that if more person in your family are telling you leave it, you as a carbon will leave that halogen at first place. So more be the branching, more is the order. You have to always learn it. So among this and this, you can obviously see branching is more, so this halogen will be leaving much easily, so it will be having more order. Some people do what? Some people start counting, sir, carbocation stability. Sir, this carbon is having 9 hyperconjugating hydrogens. This carbon is having no hyperconjugating hydrogens, because with each carbon I have attached one methyl group. So what did I say? It is an experimental logic which says for SN1, more be the branching, more is the rate of SN1 reaction. You always have to remember this. Once that is tied, then go for carbocation stability. Moving forward, although very good logic, but moving forward. Now, obviously, for leaving group, the lighter leaving group will leave early. A fatty leaving group, heavy nucleus, will not leave early. So elemental effect is also observed. Now, through chemical kinetics, we know if a reactant is in excess, then you take more of it or less of it will not affect the rate of reaction. So actually over here, what all things I have written in the reactant side, sir, alkylide and polar protic solvent, but polar protic solvent is in excess, so its concentration will do not impact the rate of reaction. So actually rate of reaction is only depending upon concentration of alkyl halide, because that is the slowest step, rate determining step. Nucleophile will get the offer of attacking when carbocation is formed, so nucleophile is more or less will not impact rate of reaction, because carbocation is only deciding. If it is formed, it will allow nucleophile to attack. If it is taking time, it will say 100 or 1000, whatever nucleophile you use, stay there, I am coming to you. So when I'll come to you, then only you'll react. So if thousands or 1 lakh of nucleophile are present, then also reaction rate will have no impact. So for SN1 reaction, rate of reaction only depends on concentration of alkyl halide raised to the power 1, because power is 1, so order of reaction will be 1. And okay, order of reaction is 1 is not written. Okay, हाँ लिखा है, it is written. It is a pseudo. Now it is written. Why pseudo first order reaction? Because actually we need polar protic solvent also, but polar protic solvent is in excess. So it is a pseudo first order reaction. That reactant is making the order of reaction only 1, because if I have to take concentration of solvent 1, then what is the power of concentration of solvent you have to take? 0, because anything raised to the power 0 is 1. Such a reaction, when there are reactants, there are more reactants, but one reactant is in excess. So through chemical kinetics, you must be knowing this, that such a reaction, although its order of reaction is 1, but it is termed as a pseudo first order reaction, where this constant and this constant becomes a new constant, which is called K dash. So order of reaction is 1, but it is an example of a pseudo first order reaction. And molecularity, what is the number of molecules that are producing carbocations are only alkyl halide, because again solvent is in excess, so it is not regarded as reactant molecules also. So theoretically, how many molecules we have? 1. So order is 1, molecularity is 1. Now moving forward, summarizing these SN1 and SN2, I know it is very important, so I'm taking time also. Summarizing SN1 and SN2, first thing, what can you say about reactivity? Rate of reactivity. Sir, which halogen better is the leaving group, faster is the substitution reaction? It can be SN1 also, it can be SN2 also. So which C bond X get broken easily? C bond I. So Ri is most effective and fast for SN reaction, for SN1 also, for SN2 also. Iodides are most reactive, and in fact, because C bond F are second period elements, bond length is very less, so no substitution substantially you see for alkyl fluorides. So for both SN1 and SN2, although mechanism is different, but reactivity of alkyl halides are same. Iodides are fastest, fluorides not even considered, so we say least is of chlorides, because fluorides we generally do not undergo substitution. Now what will be the effect of structure of carbon? Sir, we already know. For SN1, I need a stable carbocation. So generally, what degree of alkyl halide will be giving you more stable carbocations? Sir, obviously 3 degree. So that is what I have written. With tertiary alkyl halides, you predominantly have SN1, and when you have a 3 degree alkyl halide, they never undergo SN2 mechanism, because it is very bulky. And in a similar contrast, if I am not at all bulky, so who will be best possible alkyl halide for reacting via SN2? Sir, methyl halide. And therefore this methyl halide and 1 degree halide always try to undergo substitution by SN2 only. They do not try to go the substitution by SN1. Why? Because through GOC we know this also, that leave methyl, even 1 degree carbocation is not stable, it is unstable. So if I'm unstable, why I will be formed? So methyl and 1 degree halide prefers SN2, 3 degree halide prefers SN1. With 2 degree, both can be taking place by some percentage. Obviously, then solvent will decide. Protic solvent, polar protic solvent favors SN1, because ions I need. And now, so coming to solvent, polar aprotic solvent. Polar solvent I need for SN2 also. Why? Because the transition state is an ionic transition state. That ionic transition state is formed in an ionic solvent. So polar solvent I still need. But what type of polar solvent? A polar solvent which is not capable of releasing H+. Polar solvent I need because my transition state is an anionic transition state. Remember, 4-centered 3-centered 4-electron bond and electron rich transition state. So minus will be feeling more comfortable where in polar aprotic solvent. As you get H+ ions in solution, they start surrounding the nucleophile also. So because nucleophile is minus, so if solvent is having H+, then those small H+ will surround the nucleophile, and if they surround the nucleophile, then it is less available for the attack to the carbon which is not a carbocation, which is having a partial positive charge. But if I am a minus and I am not getting plus from anywhere, then such nucleophile which are present in polar aprotic solvent, they are not entertained by anybody. So they, with full speed, they only get positivity of carbon only. That is what I have written also. Polar aprotic solvent like acetone, dimethylformamide, dimethyl sulfoxide, DMSO, they are written in this format only. So polar aprotic solvent always favors what? Ions will not be formed, so SN1 can't take place in their presence. And because of these polar aprotic solvent, the nucleophile solvation. Now, if some ion is getting surrounded by the solvent molecule, it is called solvation. When water does it, it is called hydration. So because there is no H+, so solvation as in solvent is now not surrounding that nucleophile. So that is, the solvation of nucleophile is minimal. Nucleophile is not at all disturbing the solvent is not at all disturbing the nucleophile, and in fact nucleophilicity is greatest. What is nucleophilicity? Ability of a species to give electron to carbon. I am not being offered positivity by anybody, so I will be loving that partial positivity of carbon, so I'll be going mad out of it. And because of that, I will be even doing backside attack even if there is a presence of 2-degree alkyl halide. That's why I'm emphasizing on this, that polar aprotic solvent favors SN2. Now this question was actually started by, I'm giving you a question also. This question was actually initiated by JEE Advanced only. Now this is a question, this is a JEE Advanced question, I guess 2018. Now this is a alkyl halide, okay sir. The stereochemistry of the carbon is also shown to you. So this bromine is on a wedge, as in out of the plane of paper. Now, although we have not studied the reagent list, but even if that NCERT list I'll be giving you, this is a nucleophile which is not common. It is a special case. We have sodium phenoxide, so instead of oxygen I have S minus, sir. But like oxygen, that's why we read periodicity. Like O minus, it will be S minus. So this S minus will be giving electron, hence it will be a nucleophile. So we know we have a nucleophile. We have a alkyl halide. We have to do substitution. But what type of substitution? Options were only interested in the stereochemistry. What type of substitution? Sir, SN2 or SN1? Look at the solvent, DMF. Polar aprotic solvent. Polar aprotic solvent will allow, because if you look at this alkyl halide, it is not 3-degree, it is 2-degree. 3-degree predominantly does SN1. 2-degree can do this also, that also. Decided by what? Decided by solvent. Which solvent is? Polar aprotic solvent. So it will be definitely SN. So it will be definitely SN2, because polar aprotic solvent favors SN2. So this bromine will be gone, and if it is gone, then the nucleophile would be entering to the opposite orientation. So if it was wedge, the product will be formed on a dash. What is the nucleophile? Sir, sulfur and phenyl. Now, actually in that question, I've deliberately removed it because I have not discussed aryl halide, but I'm telling you that also because I mentioned it was a JEE Advanced question. So some people might search it. So I'm telling you, there was a fluorine also. But because we know, because of resonance, there is a partial double bond character. which does not break. So what reactions are we studying? Alkyl halide substitutions, because aryl halide do not react similar to that of alkyl halide, although the functional group is same, because this carbon and this halogen has a strong relation. They have partial double bond character. This bond order is very less, will not be easily broken. So reactions of aryl halides are completely different. That's why what reactions we are studying? Only of alkyl halides. What type of reactions? Substitution reactions. Moving forward, so this we have done. Now let me do this last line also. Now, what is stereospecific nature in GOC? We have discussed if the reaction is choosy about the reactant. So I'm specific about the reactant, that I'll not react with you, I'll be reacting with you. So who is stereospecific? Sir, SN2, because only backside attack is taking place. So it is 100% inversion, as in it is 100% stereospecific. But because carbocation is formed, which is planar, so I can attack from this side also, this side also. So if theoretically somebody is asking you, so SN1 is not a stereospecific, because attack can be happening from either side. So I am not specific that I'll attack from this side, not from that side. Now again, a good question, but I'm covering this question, and because we have to finish the alkyl halide also in some limited amount of time. So I've used questions as logics, not writing them that this is JEE Phala question, this is JEE that question, because that will be taking time. So I've summarized everything for you now. Let's say assign order of reaction, SN1 also, SN2 also for these. I mean, this will be quite easy for us, because this is simple methyl, this is 1 degree alkyl halide, this is 2 degree alkyl halide, this is 3 degree alkyl halide. I'm not even disturbing and mismanaging your notes, because these will be your notes also. Do not write them now. So can you tell me, if somebody is asking you that give order of, let's say, SN2, sir, it is very easy. Methyl as in A will be fastest for SN2, followed by B, then C, and least will be D. And if somebody is asking you who will undergo SN1 fastly, so sir, 3 degree will form carbocation and will only undergo SN1. So for SN1, D will be most reactive, followed by C, followed by B, and least will be A. Sir, this is very easy. Why you are telling us? This is also a type of question. Now, modifying it. Out of these four, A, B, C, D, who will now, you just tell me about SN2. Sir, in initial stages only you said, ultimately nucleophile is coming because of what? Because of positivity. What increases positivity? Electron withdrawing group. Leave about steric hindrance. Steric hindrance matters, but what dominates? First, think about the positivity. What increases positivity on carbon? Sir, electron withdrawing groups. And I guess you can clearly see this carbonyl is a very strong electron withdrawing group. So positivity of this carbon is not increased, it is much increased. What about this? This is least bulky, agreed, but here positivity is large, not large, very large. Here positivity is less, although you are least hindered, but you are not offering me some money. That guy is offering me lot of money, so I will travel Saat Samundar, I will travel oceans, but because the positivity is high, so I'll go there. Similarly, this is now this I will not even be writing it, because I told you alkyl halide undergoes SN reactions, aryl halide do not, because of, so I will not be even writing it. Obviously it will least, but why to write it? Now what about this? So this is a carbon. Phenyl also applies -I. Remember, this is not a carbocation. At this point of time there is no resonance, so because there is no resonance, so there is only inductive effect. And -I is also electron withdrawing group. I completely understand this is a strong electron withdrawing group, so it will be creating positivity to the largest extent. So rate of SN2 reaction of this A will be highest, followed by this Delhi. Now because you are least bulky, so now methyl will come, that is Bombay. And I'm not even writing C, because aryl halide do not give SN reaction similar to alkyl halide. So why to write? Because I know it will be weakest, but why to write? Now coming to this last question, again that logic, you are loser, so do not come. First let us do it for SN2. You are loser, so do not come. Now Sir, this is CH2, so minus I of phenyl. This is one phenyl. This is okay. Phenyl is minus I of 3 conjugated alkene. This is actually a minus I of at least one alkene. So obviously this will be more, this will be less. Now, what about this? Sir, this is simple. This is simple as in there is no minus I, so this is simple 1 degree. So because it is having electron withdrawing nature, so fastest SN2 will be given by this because electronic effect. After that, this guy, because minus I of alkene will also be operational. So B. After that, A. And again, I'm not even writing this. But if somebody is asking you about SN1, generally what student do is, sir, SN1, SN2, they are opposite. Ultimately, nucleophile is coming what? Why? Because of positivity. Do not only think of steric hindrance, because over here this has already lost the battle for SN1 also, SN2 also. If you compare them, you just see their degree is more or less same. So sir, if degree is same, then actually do not look at steric hindrance first, look at the electronic factor. That's what we are doing. This was having positivity because of minus I of phenyl. This is having positivity because of minus I of at least one alkene. This is not having any positivity. So who will be attracting nucleophile to the largest extent? Either for SN1, either for SN2. So for SN1 also, order will be same. So quickly moving to the list of reagents and the nucleophile that they produce, which have the capacity to replace the halogen as leaving group and forms the product, because as I have said in the initial side, weak bases are good leaving group and halogen becomes a weak base, hence a better leaving group than what all nucleophiles. So let us compare, because this is the classic reagent list of NCERT which you should know, and number of questions are asked from this. Now the first reagent, the very famous NaOH and KOH, obviously the nucleophile that they will give will be OH minus. So after identifying the nucleophile, what you do is replace this halogen, substitute that halogen with the nucleophile. So what class of product as RNU you get? Sir, ROH, because this OH minus will be going to that carbon. So this is easy. So what class of product you have? The product is a type of alcohol. Now let's say, sir, even we can have neutral nucleophiles. Yes, because nucleophile is a species which is electron rich. So even if you take water, the lone pair of electrons present in water, in oxygen of water, makes it a electron rich species. So this electron rich oxygen also can donate electron. Once oxygen will donate the electron, it will get protonated and it will snatch away the electron of smaller hydrogen. So H1H will be released in form of H plus. So that H plus and this X minus will be eliminated. And again, what class of product you get? Alcohol. So, I mean, this is just an easy case, but you should remember all these reagents and the nucleophile. In the first case, nucleophile was a charged species. In the second case, nucleophile is a neutral species. Now, similarly, let's say you have sodium alkoxide. So here nucleophile will be RO minus, even a stronger base than OH minus. If you use NaI, you already know this is Finkelstein. So I minus, and we know I minus, substitute those Cl minus and Br minus, the Finkelstein reaction. If I take ammonia, again the nucleophile is again neutral, but nitrogen will give electrons, snatch away one electron from hydrogen. So what will be it substituted as? Subtract one hydrogen, so you will get NH2. So NH2 will be substituted to the alkyl group, hence you will form your 1 degree amine. Sir, but 1 degree amine also has lone pair, so 1 degree amine also can act as nucleophile. If this acts as a nucleophile, then it will form a 2 degree or a secondary amine. Similarly, if you have secondary amine, then it will form a tertiary amine. If you have a tertiary amine, it forms a quaternary ammonium salt, and then it will stop. Although quaternary ammonium salt not there, but it is there in amines chapter, so common sense. Now moving forward. Now moving forward to the set of two reagents, KCN and AgCN, and also the later one. But first talk about them. Now KCN and ACN as AgCN, as you can, I mean, this is a common sense of chemical bonding. Sir, D block metal forms salt which are largely covalent in nature. So we very well know AgCN is a covalent salt, and covalent salt is covalent. That means it will not easily ionize. So if AgCN has high covalent nature, what will be the active nucleophile that it will be furnishing? Sir, the complete molecule will be coming because it is a covalent salt, hence not dissociating. So if you write AgCN, you will only be having electron density at nitrogen. So who can act as an active nucleophile? Only the lone pair of electron on nitrogen. So because only nitrogen can donate its electron, therefore once nitrogen will donate these electrons to alkyl group, obviously after donation it will snatch electron from the metal and will be added from the site of nitrogen. So the class of product that you will be having is the alkyl group of alkyl halide will be attached with this nitrogen. So the product will be a beautiful isocyanide. While if you take KCN or NaCN, then these alkali metal cations will form an ionic salt. Sir, ionic salt produces ions. So K plus and Cn minus ions. That means you have complete Cn minus as your nucleophile. So if you draw the Lewis structure of Cn minus ion, you can find lone pair of electrons on carbon also and on nitrogen also. Moreover, a charged species is always a better donor. So who is having an excess of charge? Carbon. Icing on the cake, carbon is much electropositive also with respect to nitrogen. So although both of them has got excess lone pair of electrons, but the lone pair of electron on carbon is actually excess of electron, is actually a formal charge. So this is a better donor. So in this case, when you have taken an ionic salt, obviously C will be donating to that alkyl group, and hence the class of product that you will be getting is this: the alkyl group of alkyl halide will be getting attached with the carbon of Cn minus of the cyanide ion. So what is the class of product that you will be getting? Your functional group cyanide, which is also termed as the triple bonded nitrogen. The suffix is nitrile. So actually class of product is a nitrile functional group. Now this becomes the definition of the nucleophile, which is called an ambident nucleophile. Now what is an ambident nucleophile? A nucleophile which has two different donor atoms in the same species, but at one point of time only one donor atom becomes active while the other donor atoms do not become active at that point of time. So what is an ambident nucleophile? Like Cn minus ion, when it was actually in form of Cn minus ion, who was the donor atom? Carbon. But when it was actually associated in form of AgCN, who was the donor atom? Nitrogen. So such a nucleophile which can ligate or donate with different donor sites, but one donor site becomes active at one point of time is called an ambident nucleophile. I have repeated this definition 3 times. Important. Now, so do we have another example? Yes. Which one? The NO2 minus ion. But again, the minus ion will only be given when you take an ionic salt. So let's say you have KNO2. KNO2 will be dissociating as K plus and NO2 minus. What will be the structure of NO2 minus this? So this here the nucleophile is charged. Who is having excess of electron? Oxygen. If somebody is having excess of electron, then don't see their electronegativity. Why? Because if someone is having a formal charge, then more be the charge, better is the donor, because attraction is nothing but plus minus attraction. So who will be getting attracted more? Who will be having more charge? So because in case of ionic salt, this O oxygen is having actual formal charge, so this will be doing the job of being the donor atom. Therefore R will be connected with oxygen of NO2, and this class of product is called nitrite. Mind you, triple bonded N functional group is nitrile with a LE, while this is nitrite with a TE, already written. NCRT fact, beautiful facts. Now again same logic. If you have silver nitrite, then silver nitrite is a covalent salt. So drawing the structure of the covalent salts are now No one is having any formal charge. Now we'll compare. Oxygen also have lone pair, nitrogen also have lone pair. Who will donate? Now no one is having formal charge, so nitrogen, because relatively nitrogen is electropositive, although not electropositive, but oxygen is more electronegative than nitrogen. So who will be donating in case of AgNO2? Certain lone pair of nitrogen. So this becomes your active site. So the alkyl group of alkyl halide gets attached with nitrogen of NO2, and hence this class of product is known as nitro group, which I guess we already know. So this becomes a nitroalkane. Moving forward, if I have silver salt of carboxylic acid, so salt is a salt, and silver salt of carboxylic acid is actually a compound which will ionize also, unlike the ambident nucleophiles examples we have taken. So if this ionizes, sir, we should learn this. Yes, definitely. I mean, it's a common sense also, because carboxylic acid salts are generally strong electrolytes. So carboxylic acid salt become a strong electrolyte, so will furnish ion. What will be the ion? Sir, RCOO minus. I mean, any alkyl group in NCERT has written it as R dash, in order to show that the R of the alkyl halide and the R dash of the carboxylic acid group may be same, may be different. But who will be acting as nucleophile? The complete RCOO minus, a charged nucleophile. So this minus will be getting attached with R and will forming a functional group called ester. Beautiful example. Now, what about the strongest reducing agent, lithium aluminum hydride? It also furnishes what? H minus. So H minus will be acting as nucleophile, and R, when substituted with H minus, will get alkane of the form RH. Last one, if you have any metal connected with R, metals are electropositive with respect to carbon. So if metal carbonyls or metal carbon compounds are there, which are generally called organometallic compounds, then in comparison to metal, carbon becomes electronegative. So what is released? That R dash minus, carbon minus, is released as a nucleophile, because metal are donor, they give electron to everybody. So this alkyl group becomes the nucleophile, and if this R dash minus attack the carbon chain, so it forms a higher alkane of the form R bond R dash. Now the NCERT facts are done. I've used that table, very, very important table. I have iterated the whole table. You have to see that table at least 2-3 times. It will get inside your head. You will get number of questions on that. Now, 2 reagents I'm adding more. First one being sodium alkynide. If you have a terminal alkyne, we know terminal alkyne carbon, this carbon is sp hybridized, and this sp hybridized carbon is even more electronegative than nitrogen. So if terminal alkyne is having hydrogen, that hydrogen becomes acidic. We have seen this in alkynes, and it will form sodium salt of carboxylic acid, again a salt, because salt, so it will also be dissociating as ion. So we will be getting this R dash C double bonded C as an alkyne with a negative charge. If this goes to the alkyl group of alkyl halide, then again it will also form a higher alkane. Higher alkyne. I mean, this C minus will be acting as a nucleophile and substituting the halogen and forming a higher alkyne. These all are reactions are important for conversions of your boards also, and many times asked by mains also. Now, last becomes, sir, if you use NaOH, so can we use NaSH? Yes, because that will give us nucleophile SH minus, and SH minus when substituted to a alkyl group will form not alcohol but thiol. So the functional group are known as thiols. Now, moving forward, sir, substitution reaction of alkyl halides done. Yes, done. Thank you. Thank God. Now, almost finishing the chapter. After substitution, we are moving to elimination, which we have already done while hydrocarbon alkenes chapter. So I'm again iterating it, but I'm giving you the basic revision I'm giving you here. If you want to, and mind you, this revision will make your JEE mains question. But if good question is coming, then you should go to hydrocarbons, alkenes. Over there, I have discussed this is in great detail. So please do that. Now, for basic questions, I'm doing everything revision. Now, alkyl halide can undergo elimination also. How? Sir, if I use a base, now a strong base, OH minus, we have just seen it's a nucleophile. What does nucleophile do? Nucleophile give electron to carbon. But if I use a stronger base than OH minus, like with O, if I connect an alkyl group, then RO minus alkoxide ion becomes a more stronger nucleophile. In fact, a more stronger base. And a more stronger base, instead of substitution, they prefer elimination. Why? Because a stronger base wants to give electron, but electron to whom? To hydrogen. Because my intention is only to give electron. And if someone is available to take that electron, then mechanism is basically plus minus attraction. So if some plus is interested in my minus, and if I am that strong base, so I'll just give away my electron to the first person, to the simplest person. And who becomes the simplest atom? Hydrogen is the smallest atom. So this is a common sense also, that whenever we have strong base, elimination or elimination dominates over substitution, and in those cases substitution doesn't take place. Now let's say how we represent that. I'm giving you a stronger base, alcoholic KOH. Aqueous KOH will give OH minus, alcoholic KOH will give RO minus. So that RO minus will be doing what? Functional group connected with carbon is known as alpha carbon. Carbon next to alpha carbon is known as beta carbon. The strong base offers electron to beta hydrogen. As soon as those electrons are offered, this hydrogen is removed in form of H plus, leaving its electrons. Those electrons is supplied to the alpha carbon. As soon as alpha carbon receives those electrons, at the same point of time, halogen is given the electron which it is demanding, because halogen is more electronegative. So this X is released in form of X minus. It will be gone with K plus, so we will be getting KX, the potassium halide, as the byproduct. Now RO minus along with that H will form ROH. What is the actual organic product? Sir, whatever free valencies we will have will still be there, but this sigma bond of C bond H has now recently turned into a pi bond between C bond C, and you get your beautiful alkene. This mechanism is known as beta elimination. It is also termed as E2 mechanism. Why? Because this is a single step process and its molecularity is 2. Order is also 2, because more be the alkyl halide, more faster will be the rate of reaction, and more will be the concentration of base, more will be the rate of reaction. So it is depending upon both the molecules. So just like SN2, E2 is also second order with molecularity 2. Now, generally alkyl halide undergoes elimination with beta elimination only. But we also know, we have also seen in hydrocarbons, so I'm iterating those things, that even elimination can also take place, but that largely takes with alcohols. We'll be discussing even again when discussing alcohols, but we have done even elimination also in hydrocarbons. Now, coming back to these alkyl halides, do all alkyl halides undergo elimination via E2? No. One alkyl halide, which is alkyl fluorides, they also get eliminated, but they undergoes elimination via even CB, which is also a two-step process. In first step, carb anion is formed, and which is actually a fast step. And in the second step, which becomes the slowest step, that carb anion forces fluorine, because C bond F is small, forces fluorine to go away and ultimately gives rise to alkene. And because carb anion is formed, so electron withdrawing group increases rate of even CB mechanism also. Sir, why repeating all such things? Because I told you, even if you leave these things for mains, maybe 10 out of 6 times they are not asked, 4 times they are asked. Now, coming to again this alkyl halide beta elimination. if I have more than one beta carbon, this type of questions are very famous in mains also. If I have more than one beta carbon, then which beta carbon will be taken by the base? It is decided by the theoretical rule, like Markovnikov is a theoretical rule, so this is also a theoretical rule, which is Sidzev product. What is Sidzev product? Sidzev has just concluded that if you have more than one beta carbon, then take hydrogen of that carbon which is already having less hydrogen. What was the logic behind it? If hydrogen is less, then whatever alkene will be formed will be more substituted. So more substituted alkene will be more stable. But instead, what I say, like in Markovnikov, I say you see carbocation stability. So here I say you see stability of alkene, because ultimately stability of alkene is decided by what predominant effect. Resonance stabilized alkene are more stable because resonance is more stabilizing. After that, you should check hyperconjugation, because inductive many a times get tied, like over here. Let's say this is an alkyl halide. I have used a alcoholic KOH. The representation of alcoholic BH is like this. So the what is RO minus? It is over here C2H5O minus, which is a strong base. It'll dominate this reaction to undergo elimination, not substitution, that we have already discussed. So alkene will be produced. But if I take hydrogen of this left carbon, what will I be getting? 1, 2, 3, 4, 5, 6. It's a 6 carbon chain. Okay, so let me make that chain. There will be double bond between second and third carbon, clearly seen. Now, let's say if I remove this hydrogen, that one, in that case, what I'll be getting? Again, those 6 carbons, and double bond will be coming between third and fourth. Now, sir, which inductive will not help you? Moreover, Sidzev rule, take hydrogen of that beta carbon which is having less hydrogen, sir. Both are having same hydrogen 2, 2. That's why I said in most of the question this will fail. Markovnikov also and this also. So there, think of carbocation stability. Here, think of product formed alkene. It should be more stable. So which alkene is more stable? So how to calculate stability of alkene? By calculating the hyperconjugating hydrogens. This sp2 hybridized carbon is connected with this carbon. It is having 3 hydrogen. So these 3 hydrogens will give it their sigma electron, thereby stabilizing the alkene formed. This will be giving 2. So total hyperconjugating hydrogens are 5. What about this one? Total hyperconjugating hydrogens are 4. For hyperconjugating hydrogens, you have to just check the directly connected carbons to sp2 hybridized carbon of alkene. So because this is having more hyperconjugating hydrogens, so this will become your major product, while the lower one becomes your minor product. This rule is known as Sidzev rule. Sir, we always get Sidzev product? Not. No. Very rarely asked, but still famous for mains after 2023. Some sets have also asked that product. Already again discussed in alkenes, Hoffman products. How many cases of Hoffman products you have? As in when more substituted alkene is not formed in larger percentage. Why we write major product? Because this alkene is formed in a larger percentage. When more substituted alkene is not, when Sidzev product is not actually the major product. In fact, the one product that is not in accordance with Sidzev product becomes the major product, becomes the more percentage yield product. Then in those particular cases, that product is termed as Hoffman product. Although in alkenes we have discussed also that Hoffman product formed is not because some XYZ, some exceptional thing is happening. No, that is also formed because of common sense only. First case is, as we know, this elimination is always anti-elimination. So when anti-hydrogen not present, then Hoffman product is formed. In case of even CB alkyl fluorides, when there is case of conjugated alkene, because in that case you will be getting resonance stabilized alkene. So why you should form a more substituted alkene if you can form a resonance stabilized alkene. And last is when you are given with a bulky base. A bulky base prefers to give electron to that hydrogen which is least hindered. So in those four cases, what type of product you obtain? Hoffman product. I'm iterating and revising everything, but you for mains you can leave that also if you are falling very short of time and you are finding it very hard. But for all those students, I'm saying if you are actually revising your stuff, so you should go to alkenes. Have discussed everything over there. Now after elimination done. Now our last reaction is reaction with metals. Now with metals we know the mechanism is homolysis. Again, in alkanes mechanisms we have discussed, but for mains per se, essentially, even if you do not know mechanism, you will do your answer. Now what are the basic reaction when alkyl halide reacts with metal? Two reactions. Magnesium is a bivalent atom. So when you react alkyl halide with magnesium in presence of dry ether, sir, why always dry ether we take? Because if you want metal to react with organic compound, do not include water, or metal will react with water and move away. It will not be offering the electrons to the non-polar organic compounds. So whenever you use metals or their compounds, it is always favored in presence of organic solvents, so there should be no water. So use magnesium in presence of diether. Because magnesium is divalent, it will form Grignard reagent. It will come in between, because here also it will be +1, here also it will be +1, so it will attain an oxidation state of +2. Now this Grignard reagent, when added to water, so because magnesium is highly electropositive, it will be wanting all the electronegative species to be attracting this particular positive metal. So it already has this halogen. It will snatch OH of water, thereby producing H plus ion, and that H plus will be given to this R, and you will be getting beautiful alkanes. So preparation of alkanes done with mechanism revised. Now similarly, Wood's reaction free radical mechanism. If you have alkyl halide, then use sodium in presence of dry ether. What happens is you get a symmetrical alkane. This R forms a free radical and undergoes chain termination with another R of its type, and therefore symmetrical alkanes are produced. Now this finishes all of your reactions of alkyl halides. Quickly finishing the reactions of aryl halides. Aryl halides also have basic three set of reaction. Discussing the third set of reaction initially only because reaction with metals of alkyl halides also and of aryl halides also are same. Why? Sir, you said aryl halide have partial double bond character, so bond order is more, so bond length is less, so bond is strong. Homolysis do not even care your bond order is 1 or 2, because homolysis obviously is an extreme condition. So whenever metals are there, they create that extreme condition. So though they do not even care that whether your bond is strong or weak. So for reaction with metals, alkyl halide reacts in the similar fashion as aryl halides. So sir, can these aryl halides can also react with sodium? Yes, they can. This was actually discovered by a scientist, hence a naming reaction, and it is called Fittig reaction. So aryl halide reacting with sodium in presence of diether, but here we have benzene ring. So benzene radical getting chain termination with benzene radical will forming beautiful biphenyl, again done in aromatic compounds. Summing Woods and Fittig, they again named a reaction, and this is also naming reaction, which is Woods Fittig reaction. Woods used alkyl halide, Fittig did the same thing for aryl halides. So if you take both of them in presence of sodium metal, you get mixed product, which is alkyl benzene. So although you will be getting symmetrical products also, but whenever you are using different molecules, so their stoichiometric concentration will be more. So probability of having cross product will be more. Hence, I have only mentioned the major product, which will be the cross product. Now, second set of reaction is SE reaction. This also we have done in this chapter only when we were discussing preparation of alkyl and aryl halides. I'll revise that thing again. We know this halogen when connected to benzene ring, because halogen have lone pair, so they can act as plus R, but because they have empty d or empty orbitals, so they will act as minus R also. Moreover, resonance is always effective when pi bond formed is stable. With fluorine, the pi bond, the bond formation between carbon and fluorine is of 2p2p. So 2p2p bond is quite effective. 2p2p pi overlapping is quite effective, very stable. So resonance is strong. But for chlorine, it is 3p. For bromine, it is 4p. For iodine, it is 5p. As the energy difference, but for carbon, it is 2p only. So we have read this in chemical bonding also, that when dissimilar orbitals undergo overlapping, they form very weak bond. That means the pi bond formed during resonance in chlorine, bromine, iodine is not at all stable. But sir, for fluorine it is stable, but fluorine is the most electronegative element, so minus I of fluorine is not large, it is very large. Because of these factors, ultimately halogens are electron withdrawing group, discussed in aromatic compounds also, in initial slides also, and again telling you it is an electron withdrawing group. It withdraws electron from benzene ring. But if at all electrophile is created, the orientation, the directive influence of these halogens are also plus R, because they will be creating less of electron density, but that less amount also will be created where? At ortho and para position. Now, again, although this you can forget also, if you are required to compare the electron withdrawing nature, then actually chlorine becomes most electron withdrawing group, followed by fluorine, because for chlorine it is electronegative, so its minus I is operational, but its plus R is very weak. Although plus R of other elements are also weak, like bromine and iodine, but they are not very electronegative also. So because chlorine is highly electronegative and it is not at all giving electron through plus R. Why? Because 3p 2p overlap is weak. So ultimately chlorine becomes the strongest electron withdrawing group, followed by fluorine, and then by down the group you can go by electronegativity. Now, although this will not be used by, I mean, this is a good question logic, but okay, moving forward now. Sir, so we have already seen the chlorination you have during preparation of our halides. You told that if I have chlorobenzene and let's say I do chlorination, that is Cl2 in presence of Lewis acid, then Cl plus will be created. That plus will be, this is deactivated. But if at all electrophile are created, where they will be going? At ortho and para position. Which will be the major product? Para product. Why? Because steric hindrance of ortho is large. So among ortho and para becomes your major product. But sir, we from hydrocarbons, we from aromatic compounds, we know some other examples of SE reactions also. So giving that also to you, although we have done in aromatic compounds. Nitration. What is the reagent for nitration? Concentrated HNO3 and concentrated H2SO4. What is the electrophile produced? NO2 plus. So that NO2 plus will be again going at ortho and para position. Who will become the major product? Para. Why? Less steric hindrance. Next example of SE reaction is sulfonation. What is the reagent? Sometimes oleum is written, sometimes fuming sulfuric acid written, sometimes concentrated sulfuric acid and heat is written. What is formed? Sir, here electrophile is sulfur with a positive charge, which is called, which when gets substituted to the ring forms benzene sulfonic acid. So at ortho and para becomes major. So this becomes 4-chloro benzene sulfonic acid becomes your major product. The other two are Friedel-Crafts reactions. Friedel-Crafts alkylation, Friedel-Crafts acylation. Here alkyl group becomes the electrophile, here acyl group, this CH3CO and positivity on this carbonyl carbon, they become the electrophile because of presence of anhydrous AlCl3. This chlorine gets removed and they get the positivity. Attack at ortho and para position. What becomes the major product? Again the para isomer. So over here the toluenes, the para-chlorotoluene, and over here this compound has got a very famous general name and hence accepted as a IUPAC name also. It is also known as acetophenone. What is known as acetophenone? Benzene connected with COCH3. So this is an acetic acid group, this is phenyl group. So acetic acid phenyl group forming a ketone, generally termed as acetophenone. Because this journal name is so famous, it is even regarded as an IUPAC name sometimes. Now, this finishes your SE reactions. Coming to the last reactions shown by aryl halides. Sir, you said aryl halide do not show SN reaction. I am again saying aryl halides do not show SN reactions. Why? Now I am listing the reason. Reason number one, aryl halides, as we definitely know that these aryl halides involve resonance. So I'll make a few of those resonating structures. Let's say this is chlorine. Because it's a conjugated system, so it will be behaving as, although the plus R effect will be less because the pi bond fold will be weaker. But ultimately, to a smaller extent only, this chlorine will be giving its lone pair. So if it has given electrons, so this pi cloud will be moving to this carbon. So it will be getting minus. Remaining bonds are as it is. The next structure will be minus will be coming at para position. The next structure will be minus will be again coming at ortho position. The next structure will be minus will be going back to chlorine. So after drawing these structures, we can obviously see that this C bond Cl has attained partial double bond character. So bond order increased, so bond becomes strong. Because bond becomes strong, so now if the nucleophile is attacking at this carbon, it has to break a stronger bond, which is difficult to do. So why aryl halide do not react as alkyl halide towards SN reaction? First is because this bond attains a partial double bond character. Point number one. Now, what is point number two? If you shorter bond length, sir, how bond order is more, so bond length is lesser. That is also one of the case. But if you just look at the hybridization state of carbon of this carbon, we have discussed this during dipole moment also. So this sp2 hybridized carbon is electronegative. Electronegative with respect to whom? This sp3 hybridized carbon. So because this sp3 hybridized carbon is relatively electropositive, so while the electronegativity difference, because chlorine will be dragging the electron cloud towards itself, and it will be dragging much of electron cloud from the sp3 hybridized carbon, so the bond length of sp3 hybridized carbon bond chlorine will be larger, while bond length of electronegative sp2 hybridized carbon bonded chlorine will be lesser, because here this sp2 hybridized carbon will not allow the chlorine to take away the electron density to that large extent. So not gone much farther. So that means relatively closer as in bond length lesser. So this through this hybridization also you can say that bond length is less, hence not broken. Now, third point is, some people say, sir, okay, then SN2 will not take place. Ultimately, do SN1. If you do SN1, then carbocation will be coming to what? To already electronegative sp2 hybridized phenyl group. So actually, phenyl cation is not less stable, it is unstable. So next is, due to the instability of carbocation, it cannot even do SN1. And last is, ultimately, during nucleophilic substitution, who attacks nucleophile? Nucleophile is what? Electron rich. Benzene itself is what? Electron rich. So minus minus what? Minus minus repel each other. Because of these four reasons, these are theoretically many times asked by JEE. So because of these four reasons, no aryl halides show nucleophilic substitution as alkyl halide do. So whatever list of reagent we have read for alkyl halides, not valid for aromatic halides. Why? Because of so and so reasons. Now, but sir, you said alkanes are paraffins, they do not react. Yes. Sir, you are saying aryl halide, the C bond X is very stable, it will not react as alkyl halide. But if I get after those aryl halides, if I create so much vigorous condition, will they react? Definitely. So those vigorous condition was first initiated and also given a naming reaction. So the naming process is known as Dow's process. Now, what is it? What Dow did is, he used chlorobenzene. You can use any aryl halide, but this is an industrial and a naming fact, a very famous reaction. So you use chlorobenzene. Okay, sir. You use NaOH, okay, I know OH minus ion will be given, but OH minus ion is not having that energy, that capacity. I will get that energy and capacity. How? Increase temperature pressure. Learn this temperature. Increase the temperature till 350 degrees Celsius. Apply a pressure of 300 atm. So this OH minus will be pressurized to go where? To this carbon. This carbon is having delta positivity, although that delta positivity is also very less, because remember this is an sp2 hybridized carbon, so polarity is also less. But if I am giving so much of kinetic energy and pressurizing this OH minus ion, this C bond Cl will anyway be broken, because I have supplied sufficient thermal energy for this bond to be broken. So at this extreme situation, this OH minus ion gets to this carbon and forms OH, phenol. But no, sir, you have not mentioned phenol over here, because phenol is stronger acid than water. And what is the medium? Medium is basic. So acid, although phenol has formed, but in presence of base, you cannot report phenol. Instead, you've reported salt with sodium hydroxide. So this becomes sodium phenoxide. And if you want to form phenol, then you have to make the medium acidic by either washing it out or using some acid. So this is called hydrolysis, and sometimes written as H2O/H+, sometimes written as H+. Means you are removing the excess of base and thereby producing phenol. So you then get phenol, which is a naming reaction, a very famous one. Now, although sometimes in JEE also, in your boards also, you do not have to write the whole sequence of reaction. Sometimes it is also Roman number 1, whatever is formed reacts with Roman number 2. So in that case, you do not have to report the intermediate, which is sodium phenoxide in this case, and you can clearly say phenol is formed. Now, a very common, basic common sense. Sir, why this nucleophile was not initially attacking? Because we have not given this nucleophile so much of pressure. Sir, but if this nucleophile is feeling so much of attraction from carbon, will it go? Yes. So do we have a method other than increasing temperature and applying pressure? Do we have a process of increasing, do we have a process of increasing the positivity of on this carbon? Yes. Who increases positivity? Sir, electron withdrawing groups. So this becomes a very famous point. So if this chlorobenzene is substituted by electron withdrawing group, but where? Who is the strongest electron withdrawing effect? Resonance. But resonance is operational at ortho and para position, not meta. So if I add electron withdrawing group with respect to ortho and para position of chlorine, then the delta positivity of this sp2 hybridized carbon will not be increased, will be increased to much larger extent. This was thought by scientist community, and NCERT gives you the experimental detail also governing this idea. Now, initially when I was using NaOH, what temperature I was using for 350 degrees Celsius. What pressure? 300 atm pressure. You just add one NO2 at para position. Sir, it will be applying minus R and will be creating delta positivity over here. How NCERT has given this phenomena with an example. Look at the temperature, not 350, 170. So NaOH used, I still require temperature, because still bond length, partial double bond, those 4 factors are still there. But instead, once NO2 was not there, temperature was almost double of this. We even required 300 atm atmospheric pressure. Now no pressure is required, and half of the temperature is required. So efforts has been reduced. Why? Because positivity has been increased. So that point is proved, that electron withdrawing group at ortho and para position increases the reactivity of a nucleophile to be attacking. Followed by acidification, you get phenol. Although that substitution will be there, this NO2 will be there, because this is a reaction of C bond X, although aromatic C bond X. Now, so if we add more NO2, if you add NO2 at both ortho and para position, look at the temperature, much reduced from 170 till 95. Sir, if we add NO2 in all the 3 places, you do not even have to use a base. Leave about heating. You do not have to even use a base. Just add water, because positivity is increased to such a large extent that even lone pair of oxygen will be getting attracted by that positivity, will be snatching away electron of its hydrogen. So H plus will be removed and this OH will be directly getting connected to that benzene ring, giving rise to this very famous compound, which is 2,4,6 trinitrophenol, and its general name is picric acid. So let's quickly browse through some JEE mains question and check that whether we have done something or not. So this is an alkyl halide reacting with aqueous NaOH. Medium is polar. So what does polar medium suggest to you? SN1. So this chlorine will be leaving and forming a carbocation. Now this carbocation is next to a 6-membered ring. 6-membered ring is free from any type of Bayer strain or angle strain. So it will not undergo ring expansion because it is still comfortable, very stable. But the next option we provide to carbocation is to get stabilized via rearrangement. So over here it will be not having any benefit because still it is 2 degree. Over here also it will be 2 degree. But if this carbocation, let us see, this carbon is having hydrogen. So if this hydrogen is going to that carbon, so positive will be coming over here. So rearrangement will be helping this guy. Let us see how. Let's say I have a 6-membered ring. Then chlorine has left. So there's a 1, 2, 3 carbon. 3 carbons are positioned over there. Now because hydrogen has been given to this carbon in form of H minus, so this carbon will be finally gaining the carbocation. Now let us check. Obviously we can clearly see it has become a 3 degree carbocation, which is more stable. You should always check hyperconjugation also, but because now degree is only increased, so I'm directly saying it is more stable. So done. Carbocation stabilization has been done. What else? Sir, what is the nucleophile? OH minus. Remember that sheet, that chart. OH minus, then OH minus and will be coming to this carbon. So let us see to the options. Yes, Bombay. So what I'm saying is, for organic chemistry, I'm rather telling you, definitely if you are practicing, it is very, very good for you. So practicing these live JEE questions, the PYQs will be helping you like anything. The practice sheet which we have also provided to you, I am saying it is going to help you like anything. But for all those students who are learning this for the first time, or maybe you are revising, but more than 60-70% of the content you is not there in your head right now. So rather, for organic and inorganic chemistry, I'm advising you that doing more number of PYQs is not going to help for those students who do not even remember the concepts properly. So rather, remembering having the concepts and the whole structure in your mind is more productive, because with that you can easily eliminate options. So for that, what you should invest your time more in, if this alkyl halide is not, you do not remember the concepts properly, then I rather suggest, instead of doing questions, what you should do is make a 2x speed of this video and listen to it again, because it will also boost your confidence of revising the concepts by your tips. And once you are given a question paper, you will, if you remember the concepts on by your tips, you will definitely be easily eliminating the options and getting to your answer. Practicing is definitely very, very important to enhance your speed. But if you are in a state that you do not even remember the concepts very properly, so revising is more profitable for such type of students than actually practicing more and more questions. Now, moving forward, this is also a JEE mains. Now, over here, what is the, sir, only alcohol is given. No medium is mentioned, not or if you think of the medium also, if it is a medium, then who is the nucleophile? Because if we will be looking at the options, we can see alkene also. But sir, for alkene, RO minus, this is RO this is ROH, agreed. But who is a strong base? You said, sir, in presence of strong base, elimination dominates over substitution. But is it a base? Sir, it should be Ro minus. And how does alcohol become Ro minus in presence of a, a, a aqueous alkali like KOH, NaOH? Remember, alcoholic KOH. So this is just alcohol. So what we'll do, definitely not elimination. Then what? Substitution. Because it is not a base. So if it's not a base, then what it is? It is just a nucleophile. Haven't you seen in the list, sometimes we are even provided with neutral nucleophile, because nucleophile is a species which has excess of electron. So this oxygen is having excess of electron. Now, can it do SN2? Remember, only methyl and 1 degree do SN2. This is, it is 2 degree and its beta carbon is also very bulky. So obviously, sir, backside attack cannot take place. Now, this is all common sense which we are generating through theory. So definitely it will undergo SN1 because it is crowded. So this bromine will be leaving behind. Now this SN1 is not because there is presence of some polar solvent, but because the structure of the substrate is such that it will definitely undergo SN1 only. Now, so let's say this Br is gone, so we have a carbocation over here. Now again, if carbocation rearranges to that carbon, it will be 1 degree. If comes to this carbon, it will have a better degree. So this hydrogen will be going there and carbocation will be coming here. So ultimately I have, in your mind also you should do this, I have my carbocation in this carbon. It is a perfect carbocation. Now what will be the nucleophiles? Are oxygen lone pair. So it will be coming and then they'll be taking up the electrons of hydrogen and releasing hydrogen in form of H plus. So that H plus and Br minus is the byproduct. So what you have obtained now, sir, this will become an ether. So in that table which we have presented through NCERT, have we seen a nucleophile OR? No, sir. So ether, I mean ether we were getting, but it was through sodium alkoxide. It was through a salt, but here this neutral species is also behaving as a nucleophile. And just look at the option, I guess. Okay, this is alkene. Yeah, this one. So these are also JEE mains question where mains wants you to actually know the mechanism also. Moving forward, now let's try this question. This is a 2019 question. Okay, now it is specifically saying that you have to think of SN1 reaction and comment about the reactivity. Sir, for SN1 reaction, what we think of, sir? Carbocation stability. What stabilizes carbocation? Electron donating groups. So carbocation will be formed here also, here also. Okay, all carbocations are, the carbon next to benzene is called benzylic carbon. So every carbocation is resonance stabilized. So all are heroes over here. But who is a more famous hero? Who is getting more stabilization? So a carbocation requires what? Electron donating group. Now this is simple benzene. You can clearly see this is OR. So these lone pair of oxygens will be donated to the ring. So this, apart from this ring, this group will act as a plus R group. Resonance is the most strong dominating. I mean, if it is giving through plus R, it is most donating. If it is taking through minus R, it is most withdrawing. So resonance is most dominating effect. So this will stabilize the carbocation to the maximum extent. This will also stabilize, but through hyperconjugation. Number one. Number two, this guy, okay, we have this OR over here also, but resonance is always operational at ortho and para position. So this group is at para with respect to this, so resonance will be happening, but this group is meta with respect to this. So it cannot apply the resonance effect at meta position because resonance is always operational at ortho and para position, GOC. But we know also, we have made resonating structures here also, previous slides. So resonance is not operational. Then what? Look at this element, sir, oxygen. Oxygen is what, sir? Electronegative. So what? Inductive. Sir, if resonance not seen, then see the less dominating. So at meta position, it will be applying minus I. Although inductive is distance dependent, so it will not be hampering this carbocation to that extent, but still it is minus I. So electron withdrawing group will destabilize the carbocation. I'm not saying it will be unstable, but definitely less stable than these guys. And in fact, even simple benzene, because having nothing is better than having some losses. So who will be the highest and most stable carbocation? D. So these D options are good, followed by C. Okay, they are competing. And now A is better because it is actually not having any loss, and the worst will be Bombay. So just check. Moving to next question. So this next question deals with the logic involving Wood's reaction. Over here, we have alkyl halide but differently substituted halogens. Now, if this alkyl halide reacts with sodium in presence of dry ether, what would be happening? Sir, we know for the reactivity of R bond X, which C bond X get easily broken, sir, down the group bond length decides. So we definitely know because C bond Br is large, so it will be easily broken. But sir, it is having two C bond X in the same carbon. So can't it go? I mean, the homolysis over here also could be take place. Over here also could take place, and we would end up with chain termination inside the molecule. But it will result in the formation of a three-membered ring. A three-membered ring is full of bare strain. So why it will be formed? So rather, one carbon of this particular molecule, let's say this one. I mean, it's a beautiful question to actually understand the logic of GOC as well. That if at all these two carbons would have terminated the chain, then it would have produced a three-membered carbon ring, which will have bare strain. We already know this, that carbon tends to be at an angle of 109 degree 20th minute, but when it cyclizes, the bonds are forced to stay close to each other. So why will it force? Therefore, a logic of GOC is also helping us to decode such a question. And in organic knowledge also, C bond X can be broken easily, so homolysis will be done quite easily for the C bond Br, and then chain termination of two different molecules would be taking place. So this will be actually our intermediate product A. But you are not asked A in the question. You are asked this B and this C. Now I guess this C is quite easy because this is COF2. So this is just Swartz reaction, metallic fluorides. So what does Swartz reaction do? Converts chlorides and bromides to fluoride. So these two will become fluorine. So these two will become fluorine. So this is also right. This is also right. This is wrong because there is only one ring. This is wrong. So this is also JEE mains question, although the year is not. I guess this is 23-24 now. So among these two options, we definitely landed up with C. What about Bombay? Sir, it is reacting with magnesium, so it will form Grignard reagent. Sir, when this reacts with magnesium, it will result in the formation of Grignard reagent. So this A will be forming MgX. So it will be having magnesium along with Cl. Magnesium along with Cl. Now, after hydrolysis, this we have done reaction with metals. So after hydrolysis, this magnesium will be taking the negative part of the heavy water. So OD will be coming to magnesium, and this will be getting OD will be coming to magnesium, and this will be getting, instead of hydrogen, it will be getting its isotope, which is D. So over here also D, over here also D. So what organic compound we have? An alkane, a cycloalkane rather, with D and D as isotopes of hydrogen, because instead of water we have used heavy water. So a very good question of JEE mains, which you should only decode once you know some common senses of GOC as well, along with what we have done. Now, some questions about polyhalogen compounds. If a carbon contains more than one halogen atom, those compounds are called polyhalogen compounds. NCERT also mentions a few detail about them. So I'm just listing the famous questions for you. Now, what can you say about freons? Now, first, what is freon? So let us summarize something about freons. I have already given this data to you. Although not very much asked, but still you should know. Some few times they have been asked. They are all JEE mains questions. So what are freons? They are actually chlorofluorocarbons. They are formed by free radical mechanism, and they react in obviously free radical mechanism takes place in presence of sunlight. So the ozone layer that we have, these freons now these days have been quite banned because they deplete the ozone layer, because they undergo free radical homolysis and sunlight make them react very fast, very easily. So actually these freons are stable, non-toxic, non-corrosive, unreactive, and highly easily liquefiable gases. The only problem they have is because they are formed through homolysis, so they easily deplete ozone layer. So environment, because of that environmental issue of ozone layer depletion, they are now these days not used or very minimal used. But they are stable and non-toxic compounds. Now you can form number of freons, but widely used freon is industrially termed as freon 12, whose formula is CF2Cl2. Now, what are their uses? They are used as refrigerant and propellant in aerosol and foams, your deodorant and sprays. The propellant action is because of what? Because of those freons. Now, exactly as I said, they are responsible for ozone layer depletion, so not quite widely used these days. Now, so what can you? Yes, they are definitely chlorofluor. They are toxic. They cause skin cancer. No, no, no. They are stable, non-reactive. So no, skin cancer, no. They are chlorine and fluorine compounds, so no. All radicals, they undergo reaction. They are formed with homolysis, but all radicals are not called freons. I mean, freons just are formed due to free radical reaction. All radicals are not freons, and obviously it's a mains question, so it will be single correct question. The first option we already got. Moving forward. Now again, which will have maximum number of chlorine. So you need to know these compounds now. These are some famous compounds. I'm just writing. You should also know them. Just know them. What is chloral? Actually, when you form chloroform, when you oxidize ethanol, you get, when you react ethanol with chlorine, it undergoes reaction and forms chloral. Now what is chloral? The alpha carb, the what is ethanol, sir? It is an aldehyde functional group. So we'll study in this aldehyde ketones chapter also the carbon next to a functional group. So here functional group is aldehyde, so the carbon next to functional group is an alpha carbon. Its carbon is actually acidic. So if you replace all the hydrogen of this acetaldehyde with chlorine, so this becomes CCl3CHO, a very famous compound, which is further, when it reacts with base, it forms chloroform. When it reacts with phenol, it forms DDT. I'll be showing them. So this is chloral. How many chlorine chloral is having? 3. So you should know this important compound. Now gamexane, we already know C6H6Cl6. So how many chlorine it is having? 6. So right now 6 is winning. What is chloropicrin? When chloroform, what is chloroform? CHCl3. When chloroform reacts with nitric acid. Now this was also a famous reaction. I mean, not very famous, but still, because JEE mains asked, so telling you, when it reacts with nitric acid. So nitric acid and they chloroform react and dehydrate. So obviously this gives H, this gives OH. So what is left of NO, HNO3? NO2. So this CCl3 is bonded with NO2, and this is actually termed as chloropicrin, a very useful compound to prepare tear gases. So a warfare material. So important. I mean, how many chlorine it is having? 3. This is also having 3. This is having 6. And freon we have already seen, it is having 2 chlorine. So our answer is B, but this is a factual question as per polyhalogen compounds. Moving forward. Now, some uses, I told you, chemistry in everyday life. CCl4, it is a non-polar solvent and highly and extensively used as fire extinguisher. I've already given you the answer. So this is B. You should learn this. So it is used as a fire extinguisher. Who? CCl4. It's a non-polar solvent. Now, what is methylene? Remember, for dihalides, alkylene and alkylidene. So because it is methylene, so although it's not, it's alkylene is for vicinal, but if you have just one carbon, how can you make vicinal? So this is just CH2Cl2. This is for one dichloromethane has a general name of methylene chloride. Now, this methylene chloride is widely used as a paint remover. Paint, in order to remove paint, it is widely used. What is DDT? Let me give you DDT, very famous. I told you chloral, this is CCl3CHO. When chloral reacts with phenol, they undergo dehydration, and the dehydrating agent that they use is this guy, concentrated sulfuric acid, a very strong dehydrating agent. So this O and this H is removed, and we get this beautiful picture of diphenyl trichloroethane. Very famous insecticide, used to save world from malaria and such diseases by mosquitoes. So a very widely used insecticide, DDT. Now, so obviously DDT is used as a non-biodegradable. It is non-biodegradable. So these days the use of DDT has also been abolished because it is non-biodegradable. It creates pollution, permanent pollution. But at that point of time when malaria was a huge hype, so obviously it was of much importance. So DDT is a non-biodegradable insecticide. And last, Freon, we have already seen, it is used as refrigerant and in air conditioners and in your aerosols. So this is me, Gaurav Singh Arora, signing off with Alkyl and Aryl Halides. Again, I'm telling you, instead of doing more and more questions, you should invest your time in revising. So make 2x speed and learn and see this video again. If you are not comfortable with theory, if you the theory, the concepts is on your tips, then you can definitely go to attempt your questions of the practice sheet that we have been attaching with this particular session. So all the very best. We'll meet in the next session soon. Bye bye.